Okay, hi everyone. Well, welcome to another working session in our efforts to understand more about fundamental theory of physics. This is, I remind you, real-time science, so no guarantees that things will work, things will be correct. We're trying to figure stuff out. So today's topic is one that I'm pretty interested in, which is the interplay between what we're figuring out about fundamental physics and distributed computing. And there are clearly a bunch of analogies between sort of synchronization in space-time and in branch time and so on, and issues that have come up in distributed computing. So today, in addition to Jonathan Gorard, we have one sort of semi-outside guest, Tali Beynon, who was for nearly a decade a very intense contributor to a lot of things with Wolfram language. He's been taking some time off that, but he's the creator of, among other things, our dataset functionality and the initiator of our neural network stack, among other things. I'm sure I'm forgetting lots of stuff there. We also have Jesse Friedman, and we might have one or two other people joining us here. All right, so let's try and start off by talking about what the questions are. I'm gonna start sharing and stop. Let's see here. There we go. Right, good. Okay. Actually, I don't have to stop videoing, but I am going to. No, I won't. Sorry. Let me be back video there. Okay, so we're going to talk about distributed computing and kind of the question. You see, the problem is if it's hard to type and be on video at the same time. Let me sort that out. Okay. So the sort of one of the key questions in distributed computing is when you have lots of asynchronous things going on, which one happens first? There are all kinds of issues about deadlocks and synchronization mechanisms and so on. One question that I have been interested in for actually about 40 years is the question of when you do evaluations of things and you can evaluate in different orders, how does that work? So to show, I'm going to show one simple example of this. If I have something like a Fibonacci that is defined as something like this, then I define, so then the question is, if I start with f of 10, that's going to get turned into f of 9 plus f of 8. And then what happens next? Well, you could turn f of 9 into f of 8 plus f of 7. And then okay, so then we have this.
I'm not sure if we can see your screen.
Oh my gosh. Well, that would be bad. Let's see. Did I forget to share?
You appear to be sharing a black screen. There you go.
Oh.
We can see you now.
There we go.
Yeah, we're up now.
Okay. I'm so confused. All right. My apologies. Okay, what I was saying is an example that I've been interested in for a long time is this question about evaluation order. So if we define kind of a recursive Fibonacci type thing like this, the first step, it's pretty obvious what to do. The question is, at the next step, we might go f of 8 plus f of 7 here, and then plus f of 8. And then the question is, the typical thing that is done in evaluation, in recursive evaluation, is that we kind of drill down sort of the left-hand side of the tree, getting all the way to the bottom, getting all the way to f of 1 here, and then we come back up the tree and we start evaluating other pieces here. And one thing that I tried in SMP back in 1979 was to have some control of that, to have sort of an evaluation front where you could do things like combine the f of 8s at this level before you go on doing the evaluation. And so that kind of led to this question of, can one have kind of this is not distributed computing, this is within a single computation, sort of what does the evaluation front look like for recursive evaluation? And the most extreme case of that is what happens with combinators, and maybe we can talk about that a bit later. But anyway, that was one of my little motivations. And I guess the thing that I'm imagining, which may turn out to be not correct, is that there's a notion of kind of reference frames that one can use to think about the sort of programming in a certain reference frame. Thinking about when one is doing this kind of recursive evaluation or distributed evaluation, how does one think about the succession of states that the system gets into, and can one do that by using sort of ideas from physics? And then on the other side, how does one use ideas that are known in distributed computing and applying them to physics? So that was a little bit of an introduction from me. I think maybe Tali would like to say some things about thinking he's had, or Jonathan, I know, had some things he wanted to say.
Sure.
Yeah.
Hi, can you hear me?
Yes, I can indeed.
Yeah. So there are a couple of things that have struck me as particularly interesting about trying to connect the formalism that you've developed for Wolfram model and particularly multi-way systems to things that are typically studied in distributed systems. So one is, there's a famous kind of technique that's used to impose a partial order on the events that happen in the system of distributed processes that are all communicating. And that's called a vector clock. And it feels kind of similar to the lattice coordinates that come up in labeling multi-way system states. And I haven't been able to exactly kind of nail what that correspondence is, if there is one, or if there's a version of vector clocks that could be made to work there. But that's something that maybe we could discuss. We could also discuss quite straightforward correspondences that I think anyone who knows what's going on here and knows a little bit about distributed systems would notice, like notions like eventual consistency in sort of distributed systems have straightforward interpretations as causal invariance, for example.
So, okay, eventual consistency, I mean, that we think that's basically equivalent to causal invariance. We think that's basically the same idea as causal invariance. Is that true?
Mm-hmm.
I mean, and I think, so what, I mean, eventual consistency means you do all these computations in a distributed way, and eventually it doesn't matter what order you did them in. Is that correct?
Right. So a good example would be sort of parallel addition of a list of numbers, one array of numbers. Mm-hmm. You could even be writing to some shared state as you compute partial sums, and different threads could be doing that. But as long as they're writing atomically, the eventual result will match no matter what order you happen to do things in.
But so what about this shared memory thing? I mean, so you're saying, because that seems to me, I mean, in the case of the universe, so to speak, there is a data structure, which is our spatial hypergraph. And the question is, I mean, the issue is, what is the analog of that? Is that the analog of shared memory in a distributed system?
Well, I wonder. I mean, there's something weird though about RAM, which is that because it's random access, you can instantaneously write to any location, and the sort of spatial component of memory is not really that relevant. Like you'll often make writes to very kind of localized regions, and there's nothing implied about neighboring memory locations. In fact, they're irrelevant if they've been allocated from the heap. So I struggle to see how space corresponds to memory.
Right.
Yeah.
So RAM versus space with the speed of light.
Sure.
And I mean, ultimately, in a truly distributed system with distributed memory, there are constraints like speed of light constraints associated with fetching data from across the cluster, so to speak.
Sure, but there's definitely a sense that there's like a topology waiting to be brought out in practice, because although you can model RAM as just this sort of block of arbitrarily addressable memory, in practice the cache hierarchy needs to exist for things to happen quickly, and to increase performance to acceptable levels. And so there's suddenly notions of locality there, right? Like as you access memory and RAM, it gets brought into successively closer caches to the locus of computation.
Is it a geodesic ball, so to speak? I mean, what's the topology? What is the effective? What is the implied sort of geometry of memory space, so to speak, implied by the existence of caches? I suspect that caches are more like an exponential space than they are like a finite dimensional space, but I'm not sure. But I suspect that by the time, I mean, you know, I don't know. By the time you've got some, you know, people like to think of sort of interconnections between computers as being everybody can interconnect to everybody, but in practice, I think that you know, there's certainly back in the past, and I don't know what the state of this is today. There used to be plenty of examples where there was a fixed sort of hypercube architecture or something, where there's some you know, some analog of spatiality. But should we go ahead?
Sorry, Tali, can I ask a potentially quite naive question? So about this notion of you know, of the equivalence between eventual consistency and causal invariance. So I feel like I want to understand better the distinction between eventual consistency and strong eventual consistency, because my understanding was that when you have a system that has eventual consistency, there's still this conflict resolution step that you have to do, right? If you have a bunch of concurrent updates, you have to reconcile things. You actually pick which final state you're actually going to use, which is effectively like picking you know, the multi-way branch that you're defining as being that thread, you know, the particular thread of history. Have I misunderstood, or is that basically how that works?
I'm not actually sure. So I wasn't aware that there were two notions of eventual consistency, one weaker than the other. So you're saying that with strong eventual consistency, there's no need for a kind of explicit reconciliation, but with weak there is?
Exactly. So my understanding, I only looked through some papers this morning, so I don't know as much about this as you might. But it seems as though, yeah, there was this notion of strong of SEC, where the idea is if you just apply any you know, unordered sequence of updates to a particular state, or to a particular node, you're guaranteed to end up at the same node. But then there's this weaker form where you might end up with different states, but then you do this final reconciliation step, which is the place where you resolve all of the conflicts. And you say, independent of which concurrent updates got applied, we're going to pick which final state we're actually going to use. And
it feels, yeah.
Yep. Sorry. No. Go on.
I mean, I'm curious how that reconciliation step is guaranteed to be the same for all different kind of participants. Yeah. How is it?
So there seems to be, okay, again, I don't know enough about this field, but there seems to be this thing called an anti-entropy step, where you basically, so when you have a bunch of these different possible outcomes, there's some kind of exchange of data that ensures that even though they may be inequivalent, you're not going to end up with inconsistent results. And then after that sort of data exchange step, you then pick a particular final state that you're going to adopt. But I certainly want to understand that a bit better.
So I guess an example might be that if you're building lists, you might sort of sort them at the end to make sure that everyone has the same canonical version of that list.
That's a good that's a good example. That may well be what's happening.
That feels very much like a Knuth-Bendix completion operation, doesn't it?
Well, yes, exactly. That's what I was thinking. So the reason I brought this up is because I think actually this analogy may even be much deeper than you initially said, right? That I think that basically what's happening is this concept of strong eventual consistency is like our notion of kind of naturally occurring causal invariance, and this weaker form is, as you say, is basically a Knuth-Bendix completion. It's a version of our model of quantum measurement, but occurring in a concurrent system. Which that may not be, I may have misunderstood something, but I think if that's true, then that's a really, really interesting kind of correspondence.
It is, but maybe it's an opportunity for me to ask a quick question, which is that in some of the presentations that I've been reading of yours, I mean, there's a lot of material, so I might have got the wrong end of the stick here. Mm-hmm. But the operations that one applies to achieve the sort of the canonical representation of some state to do Knuth-Bendix, does that have to be one of the rewrite rules of the actual system, or is it something that you can just devise on your own? Like the sort operation might not be one of the actual database operations that some distributed system supports, but it might be the thing that you still need to achieve this canonical reconciled form at the end.
Right. There's no reason to represent it as part of the updating rule, except as a kind of notational convenience, right? So it's like in automated theorem proving systems, right? So you start from a bunch of axioms, of equational axioms or something, and then in order to make the problem of theorem proving tractable, you do this kinetics completion procedure, and you produce all of these critical pair lemmas that then allow you to prove these kind of more sophisticated theorems. Now, for notational convenience, you can represent the critical pair lemmas in the same way as you represent the axioms, but they are kind of fundamentally different things, and so it's perfectly fine to kind of separate them. In the same way, I think obviously we don't yet have a complete model of how quantum measurement works, but in our current way of thinking about this, there's the underlying rewrite rules of the system, and then there are these emergent rewrite rules that the observer introduces by performing this measurement, and we represent them in the same way because it's kind of convenient to do that. But it's perfectly fine to think of them as being separate because they are separate things. I hope that makes sense.
I mean, so the point is that these things that are these lemmas added by the observer are a matter of the observer's way of making sense of the world. They are the meta description of things, not what the underlying physics is doing. And I mean, what the analogy that you're giving here seems, it's like you've done the map, so to speak, on everything, and you're doing the reduce, and you've got a bag of stuff, but it isn't in quite the form that you want it, and then you're applying some essentially outside observer done operation on it. But let's just the thing. Look, there are a couple of things that I think it'd be useful to do. So first of all, let's try to make the dictionary of terms from distributed computing and what we think their analogs are in the physics case. That's one thing. The other thing I think it will be interesting is to try to take things we understand from physics, like reference frames, and try and apply them to distributed computing. I mean, that's the because what I'm predicting, again, for me, as I've never really programmed a truly distributed system, and it's always kind of a mess to do that, I think. And I'm wondering whether, and one of the things that's most difficult is getting in your mind what on earth is happening in this distributed system with all these different possible orderings and synchronization primitives and all these kinds of things. And so I guess that the thing that I'm wondering, the thing I'm hoping, is that there may be a way of essentially allowing people to understand distributed programming by thinking in terms of things like reference frames. And that may be crazy, but that's the idea. Tali, do you have any particular comment on that?
Well, maybe I can. I do. I think that's a worthy goal, and I've been trying to sort of build that dictionary too. I think natural questions are like, what is the singularity? And it would seem that something like deadlock does correspond to singularity because it's a state in which no one can make any more progress. What I'm less certain about is what the actual use of branchial spaces, for example. Like, does entanglement have anything interesting to tell us about the failure modes of particular distributed computations? Because after all, non-determinacy is something that you want to avoid when you're engineering a system to work robustly. But of course, that the branchial space and branch-like directions are all about exploring that and understanding it better. So I'm very curious, what can we think of?
Let me make a different claim, which is that what has been the case is that engineering systems need to try to avoid sort of the inconsistencies, the ambiguities, and so on. But maybe that's just because we don't know how to program them. Maybe there's if we had a good way to think about that process, maybe we could make much more efficient use of resources because we don't have to, because we can think through things even in the presence of sort of bulk ambiguity.
Well, I mean, a very intriguing idea there is like, if individual processes have uncertainty about what other processes have done so far, and they can't make progress without resolving that uncertainty, it could be entirely legitimate for them to do both things, right? To explore both possibilities locally until information arrives from outside, from other nodes, to explain what did happen. And then progress is still being made. I mean, it's very similar to when CPUs do speculation. Like, they're retrieving stuff from RAM, but it takes tens of thousands of cycles in some cases for those results to come back into the CPU's registers. And in the meantime, instead of just twiddling its thumbs, the CPU will actually guess what the result would be. Like, if there's a branch, it'll try to predict what that whether the branch would be taken or not when results actually do arrive, and then execute what it thought would happen. And you can kind of, it would be very interesting to think what that corresponds to. Like what would, it's a performance thing, obviously. It's not changing the results of the system, but it's a whole handle on dealing with kind of spatial non-locality, right?
Right. So, this obviously brings up the consensus in blockchains as another area where one's got this notion of, things happening and there's eventual consistency, so to speak. I don't know how to think about that in this context either. In other words, you've got, ultimately you want a consistent ledger of what happened in the world in a blockchain, but yet things might be, events might be going on in different places that in that case, some of these, for example, the NKN network system that uses essentially majority vote cellular automata to try to get consistency. It feels a little bit like this also. Again, another one to understand. But let's try to go back to this dictionary. And also I want to, I don't know what the best place to look up vector clocks is, because I don't understand anything about vector clocks. I'm just going to pull up the Wikipedia page for vector clocks here. See whether I can at least understand roughly what they are. Can you describe, can somebody describe here what a vector clock is?
It's a beautifully simple idea. So it's a way of kind of computing, in a sense, a bound on the causal influence of other processes for a given processor. So basically, whenever a processor communicates with other processors, it can get their opinion of the kind of global time. That global time doesn't have to be accurate for any one processor, but it'll be accurate to the point that it matters. So if there is any causal relationship between two processes, then the vector clock maintained by both of them will tell them what the time ordering relationship is, like what events happened before, what other events that they could both observe, right? That's the cool property that they have.
So it's propagating a forward light curve, right?
I think it's a kind of a way of keeping track of everyone's proper time. That's how I would think about it. So anytime two processes interact, they update their opinions of each other's proper time to be consistent with each other at that moment. And that means that anytime and of course, the whole point is that every time you communicate with another processor, you send your opinion of what the global proper time is, and that gets merged in with that other processor's global time. So you can be inconsistent with other processes, but you won't be able to tell because you're causally disconnected from them. It's a very simple idea. Like, I'm making it sound way more complicated than it really is.
But so what happens if they later come into causal contact and they're inconsistent? What do they do?
They take the max. So the one that receives a signal from the other, that every message is accompanied by the vector clock of that processor, of the sender. And so when a receiver receives a message, it will just take the element-wise maximum of its vector clock with the sender's vector clock. Essentially, the vector clock is just a set of proper times, and each proper time corresponds to the ith proper time corresponds to the ith processor's proper time. Right? The ith component of the vector clock is the ith processor's proper time. But of course, processor all the way over here has no idea what the proper time of a processor all the way over here is until it talks to it, and then it makes it consistent by taking the max.
In this case, so let's just bring up a typical causal graph here. So what you're saying is each one of these things, each one of these events would correspond to a clock resetting event for but I'm not quite sure what the processors, what the underlying processor elements are, because these
so that's why it's hard, right? That's where the mapping becomes difficult, because things have to have an identity from time step to time step. And with the kind of fully general Wolfram model, I don't see, you can talk about little space-time patches maybe, or space-like patches, I suppose.
Right, but okay, so this is a notion where a piece of space, a piece of the hypergraph basically maintains information on essentially, it maintains a valid possible foliation here, which right, because what these numbers represent, I assume, is a possible total ordering that has been deduced from the causal graph.
Yes. So it's a foliation that could not be invalidated from the perspective of that particular patch. It's valid from that patch's point of view.
Okay, so it's a local, so this is something we haven't really thought about. It's a local total ordering that is not necessarily a global total ordering. So thinking about that in terms of foliations or in terms of general relativity, for example, what is the analog of a local total ordering? That's like a coordinate patch where things are, I mean, in terms of the hyperbolicity story of general relativity or something, that's a place where there is local sort of forward motion of time, but it might not agree with other parts of the space-time. Is that right?
Jonathan? Well, that's my understanding. I mean, that was kind of why I was trying to understand exactly how the signaling process works. Because if I'm understanding correctly, right? So it's basically like, you have some localized structure in space-time, and it's signaling by propagating out a forward light cone. And within that light cone is information about its own kind of internal logical clock. And then when that light pulse is received by a different localized space-time structure, it updates its own time. It updates its vector clock by just taking the maximum of the element that's in the vector clock and that element that it just received.
But crucially, that the vector clock that every patch is maintaining represents not just the logical time for that patch, but for all other patches in space.
Or all other patches in space?
No,
or
all those patches that it knows about.
Sure. Yeah. I mean, most of them might be zero, right?
Right. So it's some kind of analog. It's similar to, but not quite equivalent to, this kind of geodesic normal coordinates thing that you might use in GR.
Can you explain what that is? I don't know what that is.
Okay, yeah, let's talk about that.
It's not quite the same. There's probably a better way of thinking. Oh no, there's certainly a better way of thinking about it, but that's the closest thing I can currently think of. Where you're basically, so in geodesic normal coordinates, you're choosing a local coordinate frame so that all of your geodesics just become straight lines going through the origin. But crucially, it requires knowing about only geodesics that are causally connected with you, right? So it's a choice of coordinate frame that really only applies to your causal patch, and you don't really care about what's going on outside. And it seems like what these vector clocks are doing is something quite similar, right? They care about the light cones that have intersected with it and which are therefore causally connected with it, but it's completely agnostic to everything that's going on in the rest of the system.
Yeah.
Okay, but what's the analog? I mean, coordinate patches in, for example, when you're looking at a black hole solution to general relativity, and you have a coordinate system that works in some part of the space but doesn't work in other parts of the space. I think it happens in the Kerr solution, if I'm not mistaken. What can you?
Right. Well, I mean, at a very trivial level, it happens in all of GR that you're for a sufficiently small region of space, you can describe everything as SR, right? This is the notion of local Lorentz covariance. There are all kinds of instances of this where you can define a Minkowski coordinate system in general relativity as long as your spatial patch or space-time patch is sufficiently small.
Right, but so what is the physics of what's happening when you've defined that? You define that. I mean, it's a connection type thing, right? If you have a little local patch that is the Minkowski, Minkowskian local patch, and you're trying to translate that through a covariant derivative, basically, to another local patch. Is that not correct?
Yeah, right. I mean, so because this gets into the point about the most general notion of curvature, the most general definition of curvature in differential geometry is that it's measuring how much your connection fails to be exact. So, in other words, if for any such connection that you pick, for any coordinate frame that you pick, if you're in a space-time that's curved, outside of that little localized region, it's going to fail successively to be exact because there's curvature, and that's what curvature means.
Right, but so people are asking on our live stream, what are we trying to achieve here? Let me remind people of this. The point is that there seem to be very close analogies between issues that have come up in distributed computing and issues that come up in our model of physics, and we're trying to understand what we can learn from distributed computing for physics and what distributed computing can learn from the way of thinking about things in physics about possibly a different approach to programming in distributed computing. And I think what we're talking about right now is this particular notion of vector clocks, which is a way of essentially maintaining a consistent time coordinate across a distributed system. Because in general, if we have a distributed system where we've got 10,000 computers that are doing things, There's no, I mean, so let's just review what sort of the most obvious things are. I mean, the most obvious things are various kinds of synchronization primitives and, you know, various locking, critical sections, all this kind of thing. Let's do the basics of what are the analogs of those things in our physics setup. So what's the analog? I mean, you know, first question is, you've got this distributed computation going on, just like we've got all these distributed updates going on in the spatial hypergraph. What, you know, the question of synchronization is the question of defining a foliation, defining a notion of simultaneity in time across those different updates. So can we make that more precise?
I mean, there's a lot of things fall under the umbrella of synchronization. So, like, for example, if two threads synchronize, they perform some operation that allows them to make guarantees about the relative order of events in their futures, right? So, like a very simple form of synchronization, it's really easy to understand as a barrier. So you can think of a barrier as like a little surface that threads of computation will accumulate at until they've all reached it, and then they all proceed together from into the future.
All right, so let's take that as an example, right? So that's a foliation where basically what's happening is we've got a bunch of kind of threads of evaluation that are being. What does that look like? What does that look like in this picture?
I think they're bottlenecked, right? I think there's.
Do they freeze time until they all are lined up?
Surely it's like, sorry, go on.
No, you go ahead.
I was just going to say, surely it's just you have some like arbitrarily curvy looking foliation, and then you put kind of a wall so that when that foliation evolves and hits that, you know, when the hypersurface evolves and hits that wall, the bits that are sort of at the wall get frozen in time, and so eventually the foliation flattens out and the whole thing can continue.
Yeah,
isn't that basically the picture?
Mm-hmm.
Is that right? Can we draw the? I don't think I can draw this very well, but say that again. I didn't quite understand that.
So you have some very, very sort of convoluted looking foliation potentially, because things are very far out of
picture of a convoluted foliation. Let me just find a picture of a convoluted foliation.
I'm sure we have a bunch. Certainly in the multi-way case, we have loads.
Yeah, let's see. I think this one might be. Oh God, this is a big complicated mess to even generate the thing. Let's see whether we can generate it. Okay, well there at least we got.
Right. So we have one of those purple things, and it's doing some weird stuff. And then, so for instance, at the bottom, I think what Tali is basically saying is that we can have a horizontal line there, and we say we're just going to freeze time at that point. So when anything on that foliation that reaches that bottom line gets frozen until effectively the foliation flattens out, and then you can keep going.
Okay, what does this really look like, and what does that correspond to physically?
Sorry, go ahead.
No,
go on,
you
Jesse.
Okay, yeah. Just in the in your blog post, the image right below the one that you just pasted in, I think, looks somewhat like what we're talking about.
Mess. What a mess. Well, at least the code runs. That's a good sign.
Actually, yeah, that's a good point. So yeah, the thing. If we ignore the singularity, then this is an example of something. Well, actually, these are all basically flat, even though they're.
So I'm still not understanding. So what you're saying is you're waiting until everybody is ready. All the threads have reached some point. You know, sort of all the pieces of the universe have computed, have reached some state of computation, and then you kind of release time to move forward a step. You're saying, let's stop. You know, let's consider it not to. Time hasn't yet moved forward because not all the pieces of the universe have gotten updated yet. Is that right? But then what is that? What is the physical analog of that? I mean, see, one of the things that I think is interesting is in physics, the set of reference frames one considers, you know, one has inertial frames in space-time, which are basically flat foliations. One has maybe accelerated frames. In the quantum mechanical case, what we're identifying is that there are different kinds of frames that correspond to qubits and quantum measurements and things like this. So one question would be, from distributed computing, what is the lexicon of useful frames that comes out from distributed computing?
Sure, yeah. Well, here's a point that's on the way there, but it's a very simple point, but I think it's good to keep in mind. And that is that branching is indeterminacy, at least temporarily, right?
Mm-hmm.
The enemy of the systems we engineer now. And synchronization is how you resolve indeterminacy, or at least how you prevent it. So a barrier is a good example of making sure that you've kind of, and I think someone said this in the chat, this is exactly right. You've ensured that a whole bunch of different branches have all resolved to the same state. I think that's what this example of a barrier looks like.
Right. Although,
which is kind of saying that if you flatten out, if you have a causal non-invariant system, you can then flattening out your reference frame is like going back onto, basically, if you start from a flat reference frame and then you kind of develop a curved one, you're deviating from your original branch on the multi-way system. But if you flatten out the reference frame, that's one way of getting back to the original branch, right?
I'm not understanding that. What's the? I'm still a little bit confused about the sort of physics of what's going on when you're talking about. What's
going on when you physically? What's going on when you flatten out a frame is, or one way you could achieve the same effect is you're saying, suppose you're in a gravitational field. Now what? So in effect, we have some bizarre curvy-looking sort of foliation of space-time. Now let's set up a state of motion, a state of acceleration across space-time that makes that gravitational field appear to go away.
Yes.
So then you've got a flat foliation, which you can do because of the equivalence principle.
And what's your claim? Your claim is that if you do that kind of weird zipping around the universe to avoid the appearance of gravitational field,
then as long as your state of motion, as long as you maintain that state of motion to ensure that your frame is flat, then all your clocks can be synchronized. Then you don't have this problem of gravitational fields messing up your clock synchronization.
Okay, so that is the claim. The claim is that when we engineer things in a computational system to have all threads synchronized, that corresponds somehow to this weird idea of zipping around the universe to try and essentially make it feel like there's no gravitational field. I mean, that's
or conversely, if you think it's a less weird idea, you could imagine, the converse thing, right? That there's already stuff zipping around the universe, but we want to set up a gravitational field to make it look like nothing's accelerating.
It's an odd concept.
Well, they're both quite weird, but
right. But see that what's funny about that is it's but let's also look at the quantum case, because that case, I mean, one of the things that we have to get used to in this model is the fact that the natural reference frames in the quantum case are very different from the natural reference frames in the space-time case. And this distributed computing case is yet another case where the natural reference frames are completely different. I mean, what's another natural reference frame for the computing case beyond the, everything gets synchronized, so to speak? Is there one? And is there an analog of, for example, we're not maintaining the entangled state is not being in classical distributed computing. We're not thinking about entangled states. We're thinking about states where we insist on synchronization. What is the analog? Okay, the next naive question for me is, in a quantum computer, what is the analog of synchronization? Because
isn't measurement the because I mean the unitary evolution part is just like it's linear. It doesn't matter what, you can't mess it up, right?
Well, but it also is full of entanglements. And the question, I mean, in order to have an interest in quantum computation, you have to have those kinds of entanglements. But I think,
yeah, but I mean, as Tali said, the fact that you have unitary evolution kind of saves you a bit, and it's I can imagine this question could be much more significant in the case of one-way quantum computers, where these quantum computers where you start from a maximally entangled cluster state or resource state, and then you apply single qubit measurement operations. So then you don't have reversibility, and suddenly the order in which you apply those measurement operations can actually matter. And particularly if you have measurement operations that kind of are interdependent on each other, then you start to get these kind of causal dependency issues. But at least in the quantum computing case, I'm not aware of. I personally haven't seen any literature about synchronization, but it's a good question.
Okay, can we go back to our attempt to make the dictionary? So Tali identified,
actually,
indeterminacy. Go ahead.
Yeah, sorry. On the indeterminacy question. So, Tali, again, this is probably a very naive question. So, in theory of distributed computing, right? One of the really important things, as I understand it, is being things continuing to work even when you have failure of independent components. Is that a fair statement?
Sure. Yeah.
Right. So in our model, it seems that the analog of that is you basically want to maintain something like causal invariance, or at least some kind of causal consistency, even when basically some updates didn't get applied. Would that be a fair? So there was an update that was kind of scheduled to happen, and then it didn't happen, but somehow we want the causal graph to not. It may not be the same, but we don't want it to be too different as a result of that event not happening. Would that be a fair kind of translation?
Sure, and there could be situations where there's a quorum. So by introducing redundancy, you reduce the probability that you'll get the wrong result at the end, or the system will crash. But you haven't eliminated it. You've just multiplied it or squared it or whatever.
Mm-hmm. Right. But that seems very much like multi-way evolution. That once you're in the business of basically saying there was an event that could have been applied here, but it wasn't, but it's okay because we still get the same answer. Suddenly that seems a lot like statements about convergences of geodesics in the multi-way evolution graph and things like this. And I can't help shaking the feeling, because it's all there may also be a connection. And again, I'm not sure how if this is a bad kind of way of thinking about it, but there may also be a relation to these notions of multi-way singularities, right? So when you have a multi-way evolution and suddenly there's a normal form, and so your reference frame kind of bunches up around it, as you see in the picture we had above, right? We can think of that as there were a bunch of updates being applied, and then suddenly something failed and the updates are no longer being applied. And somehow the system has to be able to correct for that and still go on evolving, and the results can't be too disastrous. And so I wonder, again, if there's a connection between this notion we have about multi-way singularities, which is related, as Stephen said, both to quantum measurement and to these notions of qubits and pure quantum states. If that idea is in some way connected to kind of failure tolerance in distributed computing.
No, I think that's absolutely right. And I had a similar thought that you can imagine a message not being delivered as simply a message that gets delivered at t equals infinity or whatever,
right,
just freeze at that point. But that's not something that what I'm curious about is that you do eventually have to explore that there's something underlying this that I'm not happy with, and maybe we can think about this a little bit in the back of our heads, and that is that there's two kinds of state we have to model. There is a set of distributed processes, and they can share state, so they can be writing to some shared resource like memory or disk, but they can also be communicating over a network. You can see that as some kind of shared state, obviously. And they have internal state too. So they might have, arbitrary, the program counter and their local RAM or whatever. And the very most basic question is how do we even think that this maps onto multi-way states? Do we want to model different processes as different isolated points in some hypergraph with internal state? Are they colored vertices, or what's the general plan for how to do this mapping?
It's worth saying. Sorry, go on.
Yeah,
I was going to say it's worth saying we did consider the case of hypergraphs where the elements actually have substructure, right? Where they contain information about their causal history, and I think that's probably much more direct. That version, which we ended up not pursuing in as much detail, is probably much more closely related to the distributed computing case. But maybe Stephen has a comment on that.
I'm gonna slightly disagree with this, because I think you can think of pieces of the hypergraph as being tiny symbolic expressions. The way of thinking of the hypergraph is it's a collection of relations between elements. So the relations correspond to the hyperedges in the hypergraph and so on. And I would think that the correct model is that what's going on inside a single processor is a lump of hypergraph. It's not a single node in the hypergraph, it's a lump of hypergraph. And the fact that in this particular, in the physics case, we're really looking at right down at the level of individual elements. And so we're not aggregating it up to this big lump that we call a single processor. We're going right down to the individual bits, so to speak, inside the processors. So I think that's the right way to think about it. Is that, yeah?
I'm a little bit skeptical about that. So, maybe I'm misunderstanding something. It seems to me that there's a trade-off here, right? Because so suppose you're right. So suppose there's like our model of elementary particles, right? That these processes are just persistent localized structures in the hypergraph. Well, as Tali said, in order for these to be good models of processes, they have to be able to store non-trivial internal data. So either they have the ability to change, in which case you lose the capacity to kind of track that as a piece of as an identifiable piece of the hypergraph through time, or they don't have the ability to change, in which case they can't have non-trivial internal structure. And it seems that there's a trade-off to be made here between whether the piece of the hypergraph is identifiable through time and whether it's able to have non-trivial to make non-trivial internal representations.
Okay, so let me make a jump here. So I mean, this reminds me of kind of these different models of parallel computation. I mean, way back in the infinite past, I did some work on the connection machine computer, which was this computer where the idea was there would be very small, each individual node of a 65,000 node computer or something would do very little, but together they would be able to do lots of stuff. And so it's kind of analogous to models of fluid dynamics where you're saying the individual molecules are very simple, but somehow you'll make it up by looking at a large number of molecules. So I think there's a question of whether there's a model of computation that is sort of whether you could imagine using as a programming language something like what we have in our model of physics. I mean, that's the same kind of thing as one's trying. That's what the connection machine type idea was. It's like what programming with cellular automata is like. And so on, and that's let's see. I'm seeing some stuff here that I'm being told to compute. Let's see, what is this? Is this going to work? Oh my gosh, what is that? That is not. This is
I thought I would do a fun little translation of like one of the toy problems that's used to illustrate the kind of challenges of concurrency and deadlock and all this kind of thing, which is what's called the dining philosophers problem. And you can just imagine it as like a circular table. There are a bunch of philosophers sitting around and they have forks, but they seem to be sharing the forks. So the guy to my right has a fork to his left. It's the same as my fork, right? And I got to pick up both forks to eat. But if I pick up that fork, then he can't use it. So we sort of have to coordinate to make sure we're able to all get to eat, because these resources are contended. Now, the problem with that, so what this represents is the full set of possibilities for a kind of approximation of the dining philosophers problem, where they're at a flat table, not a round table, so it doesn't really work. It needs cyclic boundary conditions.
What happened? Why is this not working when I have just a smaller number here? Oh, I see. That's how many. Where are the philosophers here?
H is a hungry philosopher. T is thinking philosopher because he's eaten, so he's got energy.
Okay, so I mean, let's vertex. Let's label the vertices at least. Oh boy.
And underscore is a fork on the table, and carré is a fork in the hand of the neighboring philosopher.
Okay, so is this something we should be able to understand?
Well, it's not correct because it's a string rewriting system and it needs to have cyclic boundary conditions. So the point I was trying to illustrate here is that the correct model is below, it's only got two philosophers. It's the Wolfram model, right? But I found it difficult to embed the kind of essence of the problem into a hypergraph, simply because I needed to use like self edges as state. Like I wanted to color the vertices to indicate that philosophers and forks are different entities, but I couldn't really do that. So I had to use self edges to do that identification.
Right. So the question is, how do you program a hypergraph? And it's a bit of a mess. I mean, I don't recommend. I think one needs to decorate the hypergraph a bit to make it a practical programming language. The same thing happens in cellular automata. There are some things like image processing and so on where you can directly do them at the level of cellular automata, but there are others where you really need more superstructure to make it a convenient programming thing. I mean, certainly we know in this case, let's see, I had some examples I can pull it up. I had some examples here of that Max worked on also that were, like examples of Turing machine correspondence, right? Where you can have, like that's an example where, where one's using self loops basically to represent state in the Turing machine. It's not particularly beautiful. I mean, it's a useful proof, but it's not particularly beautiful. I mean, having said that, it's always amazing in the history of computing that things that start off being sort of weird, the fact that we even can represent everything we can represent, starting from the sort of low-level form, is I don't think we should absolutely give up on using self loops and things as ways to represent bits, but I don't think it's particularly elegant. Look, I just wanted to come back to the question of whether, when one is trying to model, when one's trying to make the correspondence between distributed computing and what's happening in hypergraphs, to me, this question of whether one is looking at the individual elements of the hypergraph as like whole processors or not, is, I think, the analog, what we saw in the case of things like cellular automata or these massively parallel computers. The hope was that you could kind of make up with parallelism for what you lost by lack of structure in the individual processors. And that promise never really worked out. And the reason it never worked out is because it was really hard to understand how to program the thing when you had these, there were certain things that are like, the analog of convolutional neural nets, basically, where you can have sort of the array doing things in bulk. But when it comes to sort of understanding what what's happening in sort of the truly distributed case, it seemed really hard. In fact, back in the 1980s, I tried to work on kind of graph rewrite-based languages as a way to understand what might be happening in these sort of distributed parallel systems, and I got pretty much nowhere. So I'm sort of hoping that now we can get somewhere because we have a better understanding from the correspondence with physics with what, how to think about graph rewriting. And to me, I mean, again, I keep coming back to this thing that I sort of have this feeling that the right way to think about it is in terms of, we humans tend to think sequentially. So the question is, how do we sequentialize a distributed system? And my claim is that's exactly the same thing we're doing when we make reference frames and when we define sort of simultaneity surfaces in time in these physical systems. And that, to me, seems the hopeful new direction is thinking about that correspondence.
Right, but Stephen, you do see my point that, right, if you have a localized substructure in the hypergraph, and it can take on, and it's able to have non-trivial internal representations of things. So, for instance, it could take on 1,000 different possible versions of its own substructure.
Yeah, right.
It's really hard to track that thing in time, right? The things we can track in time are almost by definition the ones that have just a single combinatorial state or a very small number of combinatorial states.
Well, we don't yet know what's exactly involved because, particles, we imagine that particles are things that have a sort of a more or less, somehow a more or less constant structure. We don't think that the nodes involved in a particle will be the same nodes over time, but we think that there will be some way to identify this is the set of sort of twistings of connections, and those are the things that are being preserved through time.
Exactly. So given that all we have fundamentally is the combinatorial structure, it doesn't seem possible that regions, that localized persistent regions of the hypergraph can store non-trivial information.
Well, what if they're little black holes and they've got all kinds of internal state? And what if they have a boundary that has some definite structure? Once you have a boundary that has a definite structure, you can know, it's a bag which can have anything inside it.
Well, yeah, but then I would argue black holes are quite hard to identify and track within these systems, basically because of the no-hair theorem.
Yes, I mean, sure, but I think that my point is, one could imagine, okay, I think it's not by no means self-evident that you can't make sort of a bag around a part of the system. Now, maybe the only way to make a bag is to make an event horizon. But my claim is that you could, if what you want to do is to have something where you are identifying some sort of persistent state in a part of the system, it seems to me that you should be able to do that by having some membrane in the system that has some definite form that you can identify. But I mean, again, I'm not claiming that. Okay, so my claim is that the way to think about this, so what I'm thinking is going to happen is that there will be a decoration of this hypergraph model that has additional sort of places where you can, handholds or something, where you can, that help you program it effectively. Just like, in a sense, this hypergraph model is like a symbolic system, like some transformations to symbolic expressions, but the symbolic expressions have no names of heads. So in other words, instead of saying, f of g of x, y, h of z goes to something or other, we are just saying everything is the same. There are no sort of separately named heads here. And my belief is that there may very well be a way of thinking about, when we decorate the hypergraph to make it something that is, in a sense, much more elaborate than physics. It just has these sort of human understandable tags in it, effectively. I mean, it's a tagged hypergraph of some kind, right?
I think the argument for, you might say that that's not pure, and that's not presumably what the physics model wants or needs, right?
Mm-hmm.
But I guess just my example of the Dining Philosophers was that, we want to build toy models that we can explore. We want to build like a double slit experiment or whatever.
Yes.
And those kind of cases, like, you really do want to hand code in some stuff and not have to mess around with like lots of degrees of freedom that are like fiddly. And you just impose structure that will get to isolate the things you care about so that you can investigate.
Right, so let's take the Dining Philosophers as an example. Let's say we want to make a clean symbolic representation of what's going on here that we can then, because you've got these strings, and that's probably not the right way to do it. You probably want transformations on symbolic expressions here rather than transformations on strings. And it's probably not difficult to see what because in a sense, our hypergraph model is the absolutely minimal kind of version of making transformations to what amount to symbolic expressions. I think Jesse was trying to say something.
Oh yeah, just I guess repeating sort of what Tali said, but I think it's an inherent property of the system that you can draw bags of as you put it of any shape or size that you want around as many or as few nodes as suits your purpose, and call that a process, call it an observer, because that's what makes the most sense for what you're trying to do.
Yeah, but so
my argument though would be that suppose you have two such things. You have two regions of hypergraph and you've drawn bags around them. As Tali says, as well as having the internal representation, you also have to have data flow. So now you have to have so it's not good enough just to have an event horizon, because you need to have causal connection from one bag to the other. And my concern is, I'm not saying it's impossible, but my concern is it's going to get really messy to be able to say which piece, when you've suddenly got a bag of causal edges and then there are causal edges between those, between one bag and another. Which bit is one bag, which bit is the other bag, which bit is the bridge? That's going to get hard to identify.
I don't disagree about any of this. My claim is that in making the correspondence with practical computing, the right way to think about that is to decorate the hypergraph with tags and so on, and to end up thinking about the hypergraph transformations as being transformations on more labeled symbolic expressions.
Yeah,
and that
I agree.
Yeah, I think we all agree.
Right. Okay. Yeah. Fine. But what I'm saying is, Could you compile that into something which is pure hypergraph? The answer is undoubtedly yes. And yes, you have a lot of sort of bag juggling to do to make that work. But that, to me, that extra compilation step is not so interesting. And I think at the level of a lot of what we've done in making the correspondence with physics, that will still apply even when we have these tagged hypergraphs. That would be the claim. And I think the thing that I'd like to understand is I just want to come back again. I want to come back to this dictionary, but I also want to mention some application cases, because I mean we've got traditional distributed computing, we've got I think we've got the blockchain case. We've also got someone on the live stream is mentioning, and it's correct, the multiplayer games case. And one of the things that I find sort of interesting about these computing cases is, our traditional model of computing has been, you give some input, system grinds away for a while, then you get output. But that's really not the story in most of these applications. And again, this question of where's the output feels like it's another one of these reference frame type questions. I may be wrong. Like in a multiplayer game, there is there's some kind of the problem is there are humans in a multiplayer game. If it was just sort of avatars playing each other, you would have a perfect causal graph, and it wouldn't matter what the sort of physical wall clock time of anything happening was. All that would matter is the interactions between these avatars. Are there other use cases, by the way? Are there other cases that we're missing here?
Well, I think it falls under distributed computing, but all of these fall under distributed computing, but databases. Clustered databases,
where the issue is consistency of updates and so on.
Yes, trying to accurately reflect the order in which events actually came in from the outside of the system.
In a clustered database.
Yes.
And how is that actually done? I should know the answer, but I don't. I mean, what is the mechanism? What is the typical mechanism? Because that's, it's again, to me, that is, you're sending out light signals to try and get synchronization, basically. Is that the way we can think about it?
I should mention that there's a piece of software called Jepsen. So various database providers make claims about what guarantees their databases can make. Do they protect against such and such kind of failure? Do they provide ACID guarantees or whatever? And Jepsen is a kind of like meat grinder that will put your database through its paces. And I think it does that by very carefully spawning all the little clusters, all the individual nodes that make up one of these distributed databases, and then tightly control how they communicate to effectively explore the full sort of state space of, or at least randomly explore the state space of orders, relative orders of message passing and that kind of thing. And it's notoriously just broken lots and lots of what were claimed to be, bulletproof kind of databases.
Well, so again, what is going on here? I mean, are these sort of weird spacetimes or something that are being tested? Is that the way we should think about this? What is the thing? Go ahead.
Yeah. There's one thing that happened as soon as I try to make too close kind of connections between these notions of consistency and Wolfram model type stuff and multi-way systems, and that is that there's this fundamental difference between reads and writes in these models. And I'm not quite sure what that looks like, whether that can be embedded in multi-way systems or whether it requires a slight elaboration of multi-way systems.
So you're saying, the point about a write is there is a shared resource. It is it's the database. It's the state of the world, so to speak. And that's different from reading, which is a non-destructive operation where you're just, where you can read as much as you want. It doesn't matter. Reading feels like it's measurement, but I may be wrong. Writing feels like it's evolution of the system. Reading feels like, but I may be incorrect, that it's like you make a quantum measurement, you make it again, you make it again, you make it again, you'll always get the same answer.
But as Tali said, it's non-destructive.
But reading also doesn't have to be the end of the story. So it could be that, like your state gets updated because you read the state of some other part of the graph.
Right.
I think it sounds much more like incoming versus outgoing causal edges.
Right, yeah.
So I think a read is when you have an incoming causal edge, and a write is when you have an outgoing one.
That
So
makes perfect sense, right? Because I mean, in fact, the way we should think about the events in the causal graph are what comes into an event is like a function. And what is coming into the event is the inputs to that function. What's going out is the output from that function.
Right. So once you're in your simultaneity surface, it doesn't matter how many incoming edges there are. It doesn't change anything. But the outgoing edges absolutely do change things that are going to happen in the future.
Okay, so that's the analog. So in our dictionary, okay, we have reads and writes, and those correspond to incoming versus outgoing causal edges. Interestingly, I mean, we have the correspondence between causal edge density and energy, which one kind of has one wonders slightly about in this respect. Don't know what that corresponds to. But again, going on with this dictionary, I mean, so, actually, this is an interesting comment from someone on the live stream. Is FinTech the multiplayer game with no humans? That's an interesting thought. I mean, multiplayer games versus, traders in a market where effectively you've got, boy, that's an odd idea where what matters, I mean, I'm just trying to wrap my head around this thought of when you have communication, each event is a trade effectively, and what you're seeing is a sequence of trades, and those trades are interacting with each other in a certain way. And you could imagine something where there are trades going on between people in one part of the market and another part of the market. Yeah, that's interesting.
So there's a fun example. So there's this thing called a race condition.
Right.
And the simplest example of that is like a data race. And that happens whenever multiple threads are all accessing the same memory location. And at least one of them is a write. That's really important, right? They can't all be reads. Every time that happens, that guarantees, I would claim, a branch pair. In fact, a branch pair for each pair of reads and writes. And that's because, depending on the relative ordering of the writes and the reads, you can get both results. The indeterminacy, that's the source of indeterminacy in concurrent programs, or one example of such a source.
What is the analog of the memory location?
It's probably just the region of hypergraph, right? Because in an ordinary hypergraph transformation system, you get a branch pair, or you get there are these trivial branch pairs that you get because of space-like separated events. But the non-trivial branch pairs you get because two updates tried to, basically update the same region of hypergraph. Like the two updates overlapped with each other. So probably the analog of a memory location is just the location in the hypergraph, right? And as soon as you get overlaps between updating events, you're guaranteed to get branch pairs.
So okay, so if this is, I buy the idea that the race condition corresponds to a branch pair. What is the multi-way graph then? Is that some kind of representation? What is the, in the study of validation of distributed systems, is there an analog of the multi-way graph? Because the multi-way graph must correspond to all possible sequences of race conditions, all possible resolutions of race conditions.
So there are tools that will actually try to detect race conditions, like Go has such a tool. But instruments reads and writes to detect concurrent attempts.
But what is the output from that? I mean, it's some kind of profiling graph. What is there? Is there
an error?
It
says there is a race condition, and then the program crashes because you should fix it. Right?
Okay. Yeah, but I mean, but so there isn't. I mean, because the thing that is really different from what we're doing in physics is that it's ambiguity really in bulk. Whereas, I mean, what you're talking about is there's a single race condition. Go fix that, What we're talking about is the whole universe is full of race conditions, so to speak. 10 to the hundreds of race conditions, so to speak.
I think we should, maybe Tali disagrees, but from my limited understanding, I think we should look into these things called Kano maps, which are a sort of Boolean algebra technique for representing and identifying race conditions.
No, well, the Kano maps usually are just part of the sort of simplification of Boolean expressions.
Right. And that's how I identify. That's how I came across them. But that I know that they're also used in identifying race conditions.
I bet that's just by virtue of the logic. I'm skeptical. Now, there are a number of comments on the live stream, and I'm okay. Dictionary edition, transactional memory. Yeah, that's a well, I mean, it's basically the transactional memory or the
But does that actually exist? Is that possible? I mean, it's an alternative to a lock. How do you have transactional, or how do you have transactions or locks on writes to space or to the spatial hypergraph?
It's kind of like throwing away the branch that didn't resolve properly, right? Like you try to resolve, and if it doesn't resolve, you just let it somehow eliminate it from the actual final result.
Though.
Well, yeah, I mean, a lock on a write is just an event horizon.
Mentioning hash graph, which is a interesting. I mean, so that's the attempt to do better than a blockchain, where it's kind of a network of transactions that can be sort of progressively resolved. And I do agree that is potentially quite relevant. I mean, this whole NKN system, which I finally understood. Let's see whether we can pull up an interesting example of a hash graph.
But hang on, wait, am I going crazy? A lock on a write is just an event horizon, right? You're just saying there can't be any causal edges coming out of this.
Then does that make a transaction? Does that make a transaction in event horizon around multiple potentially disjoint nodes in the hypergraph? Which I don't think that's possible, is it?
What are you saying?
Interesting.
I don't get this lock on a write thing. Can you?
No, I don't understand this.
Jesse just asked, what is the analog of a lock on a write, right?
No, I asked what's the analog of a transaction. If you're saying that a lock, well, no, I did ask earlier what's the analog of a lock. But if you're saying that a lock is an event horizon, then is a transaction some kind of extension of that?
Right. Well, I mean, that's what I was asking. To the extent that I understand locks, I think that aren't they just event horizons? They're saying you can't have outgoing causal edges from this state.
No, I would say that's deadlock, right? Deadlock is you hit a singularity. Well, I mean, I know they're different from event horizons.
Well, I think they're different. I think I think that this is an interesting idea, that the lock on write means no.
The state can't write to things.
Yeah, so no outgoing causal edges.
So deadlock is a kind of lock, right? But the point is, the weak cosmic censorship conjecture doesn't hold for distributed computing. You can have locks that aren't deadlocks.
No. So a lock is a data structure. It's not an event.
Right. A lock is a technique. A deadlock is a condition.
No, I understand, but the purpose of having this Boolean data structure is to ensure that you can't have writes when a particular thread can't make writes when it's in a particular state, right?
What Boolean data structure? The Kano map.
No.
Okay. So in the simplest case of, like, you have a critical section problem, the reason you introduce a lock is to ensure that if one thread goes in, another thread can't also go in, right?
Well, it just blocks. So yeah.
Right. That's the objective of the data structure. It's nothing more than just a Boolean flag that says there's someone already in here, right?
Okay, so what did we say? So I'm confused here. So first question is deadlock. So deadlock is you're stuck because you can't, you're trying to write, but something else is trying to write.
So deadlock is very easy to understand. It's like you waiting. Thread A is waiting for thread B to release a lock.
Is it like a closed time like curve?
Thread A to release a lock.
Is it like a closed time like curve?
I wouldn't say so. I would say it's mutual dependency that means that no one can make progress. So literally, there's no successor state. Like, that's why it's a singularity.
I see. Right, so you're saying this is
it's a branchial singularity, not a causal singularity, or not a strict causal singularity.
I'm not sure I understand the difference, really. I'm sorry, it's all new to me.
Well, so the difference is it the case that, yeah, I'm not getting this really. Jonathan, try explaining this again. I'm confused.
Well, so causal singularities, we still don't really understand them, right? But one feature of them that we think they have, at least in the black hole cases we've investigated, is that they can have time extent. It's just that they just have a kind of disproportionately large number of causal edges. The branchial singularity is the case where you have a normal form, right? That's the case that we had the pictures of above, where you have something that just hits a normal form, it doesn't evolve anymore. And that, I think, is what you're referring to. It's the deadlock case. Now, it happens to be that in certain conditions, a branchial singularity will imply a causal singularity, but they're not the same thing.
Well, there might be a fun implication of what you just said, which is that a different condition called a live lock is actually a causal singularity, because it's something that does have time extent. There's local progress being made, but there's literally no, that it can't affect anything. Like the rest of the program can't proceed. And so there's no causal edges out of that little cluster of live locked threads.
That's
Even
really
though there's
interesting
activity
idea.
going on inside the live lock. It's
Yeah.
burning CPU. Whereas
Yeah.
the deadlock is not burning CPU, it's just blocked.
Yeah. I want to understand what a lock is exactly. I think that's fascinating. So we would have to have at least, there's two observers or whatever, spatially kind of localized little chunks, and then some shared state. And what does a lock look like in the full multi-way graph? Because either of them can acquire the lock first, right?
Right.
And then the other one just does nothing. Isn't that the quantum harmonic oscillator that you were showing the other day?
That would probably be an example of such, of a simple lock. But one of the things, actually, so Stephen and I were talking about this over the weekend, that I was thinking, one structure that might be, for understanding things like deadlocks and mutual exclusion and so on, one structure that we haven't explored in the physics case, but I think does seem relevant to this, is something like a causal, I think Stephen referred to it as a causal exclusion graph, or I think I called it an acausal graph, right? Which is where you're saying, not you draw a directed edge between events A and B if B, if the input of B depends on the output of A, but you're saying you draw a directed edge between events A and B if B can't happen if A already happened, right? So it's some kind of inverse causal graph. It's telling you which events are mutually exclusive with which other events. And so in that case, I think the causal exclusion graph gives you a very natural way of representing a lock. Sorry, because you're just saying if this thread went in, then this other thread couldn't go in.
Wouldn't that be an effectual graph? If it's a causal graph flipped upside down.
Yes.
Yeah, I like it.
Okay, but can we actually draw one of those? And okay, we've got a number of comments here, and I'm still.
If you want to, we can easily draw one, because we just take the causal graph and then we ask which vertices aren't reachable from which other vertices, and we just draw that.
So, for example, we take this causal graph,
right, and we compute the out components. We're basically asking for a complement of the out components of each updating event, and we're drawing the graph of that.
Okay, so this is now we're talking about the causal exclusion graph, aka the effectual graph. Okay, here's our graph. Now, what do we do here? So we want to know for any one of these events, we're trying to figure out which.
You want complement vertex list out components, vertex out component of that vertex.
Wait a minute. What complement of the vertex?
For each event, you're asking what are its outcome? Which vertices are in its out component?
Yes.
And then you're taking all of the others, and you're drawing directed edges to all of the others.
Help me work through that. So you're saying,
so it's complement vertex list of that graph.
Of the whole graph? Oh
Yeah,
yeah,
I
okay,
think-
okay, I
I think so.
understand. I understand what you're saying.
And then vertex out
then-
component, yeah.
Then vertex out component of a particular vertex.
Right.
Of a particular vertex in GGG of that particular vertex hash there. And then what we want to do is map that over the vertex list of GGG. But how do we then reconstruct the graph from this? We want to say...
So then we want to say directed edge hash of that, hash that, and map.
That thing there. Although we probably want to thread that, yes?
Yes.
And we might, this will end up with a pretty complicated thing, right?
Yeah,
This
yeah.
is-
Because I mean, amongst other things, it'll obviously anything that's back in time will be part of the causal exclusion graph.
So maybe we want to get rid of the things that are back in time.
But then that gets tricky because you have to define foliations and things.
Oh my God, it's got 52,000 edges. I think we need to try a simpler case. Well, let's try, I'll tell you what, let's try the minimal case of a grid graph. Does anybody know what the, how do we get a grid graph out of this? We can do that with the sorting thing, right?
Uh-huh.
So here we can make one of these with AB goes to BA. And we get, what am I trying to do here? This is, I'm going to make a multi-way causal graph here. Is that right? Yes, that's. Is that what I want you to do, Jonathan?
I don't know. I'm not.
Well, okay. So let's just try this simpler case here. Okay, let's try that case here. See whether we can make this exclusion graph for this one here. That was extremely unexciting. Let's try it, making that a layered graph plot.
Is it
So
the A causal graph, is it something subtracted from a full graph? Is that what we expect to see?
I think so. Yeah.
Yes.
It's
full
a
graph
complete,
minus
yes.
the causal graph. Okay.
Exactly. That's a good way of thinking about it. Actually, it's just a complete graph.
Now that I understand what's going on, I'm afraid effectual graph is not an appropriate name. But I'm hoping there's something else that can be called that, because I think that's a good name.
It is a nice name.
Okay, but you're saying it's essentially the graph complement of the complete graph complemented by the actual causal graph. So it's asking, what are all the connections? What are all the things that couldn't be? But you see, but this is not the transitive closure of this. This thing is a transitive closure of, if we take this graph and we do the transitive closure graph of this, that's going to give us, right? Because this graph is just saying what can lead in one step to this.
That's a good point. Well, but the vertex outcome, that's why I did vertex out component rather than just adjacencies.
But why is that? I mean, this is the transitive closure that's showing for every event, what are all the events that it can lead to at any time.
Yes, I understand, which is what vertex out component does.
I understand, but why is this what you wanted here? Because what you would like to know, the better.
Oh, so you're saying we want the transitive reduction of the acausal graph?
Yeah, well, let's try that. Let's try finding
okay.
the transitive reduction of this. So take that and say transitive reduction. Do we even have a transitive reduction? Is that a thing? Yes, we do. Transitive reduction graph.
Beautiful.
Okay, tell me what it means. What does that mean? So that's saying...
Well, actually, no, that's just saying there's a single thread of time.
In this graph.
Right? Because that's just telling you that you can't go back in time, basically.
But why is there a loop? Let's try a bigger case.
Oh, no, wait, sorry, that wasn't the sorting rule. Okay, no,
that wasn't the sorting rule. This is a real rule that is causal invariant.
Okay, I have no idea what it means.
Should we try it for the sorting rule? Well, let's try it for this rule for a slightly bigger case. Let's try this, and then let's make the thing here, and let's make the transitive reduction graph of that. Okay, let's get to that, and then we'll do this. Well, something is going on here. There's something this is trying to tell us. And I think you're right. It's something about a single thread of time.
Right. This might be a good heuristic for, I mean, if that's true, this could be a good heuristic for causal invariance.
Well, let's try looking at, let's try getting this sorting rule thing to work. Okay, so we've got, but remember, this is now the multi-way causal graph that we've got here, whereas the other one was just a single causal graph.
Right.
So how do we deal with that?
Oh, that's okay. I mean, that's the more realistic case at some level.
All right, okay, well, fine. But let's do this then. Okay, so there's our causal graph. And now let's do the same thing here with the transitive reduction. Should make a function out of it. What the heck happened there? So this is the causal graph. Let's say
this is this thread not liking the fact that we have that our events are lists?
Well, then, if that's the case, we can make that into an index graph.
Right.
Okay, so this is, I don't know what we call this. This is a causal exclusion graph. Bad name, but let's just do this anyway. And then let's say here, causal exclusion graph of the index graph of GGG. Okay, what is going on here? Well, this is a causal invariant case. Let's try a non-causal invariant rule.
Yes.
How do we get a good non-causal? Well, here, we can enumerate possible rules and find a non-causal invariant one. Do we need to do that? What is it? Enumerate. We want, well, let's see, let's use our, let's go find our, I want to look back at this hash graph thing as well, because I think that's relevant. Just a second here. Always use our actual site to get the information. Okay, what is it called? Enumerate substitution system rules, right? That's what we want to do.
Mm-hmm. I like TKD Boy 555 suggestion of the causal graph being called the unrealized graph. It's like all the paths you couldn't take.
Oh, yeah, it's like a counterfactual graph.
Yeah, exactly. That's a good name, actually.
Well, it's not that they're unrealized; it's that they couldn't have been realized.
Yeah, the impossibility graph or something. I don't know.
Right.
Something in that.
All right, so these are possible things, and now we want to find the. Do we have a causal invariant Q?
Yeah.
So let's just okay, so let's select out of that set of select from this list of all rules. Let's select well, actually we can go ahead and say select in all rules the causal invariant ones. The causal invariant ones with respect to that initial condition. Okay, fine. So it's about half of them are causal invariant. Okay, let's compute this creature for each of these rules now. Okay, so we've got this, and we're going to make that for each of the rules, and then we're going to do a CXG of that. Okay, so we'll do this, and we'll map it over this, and we'll do the CXG of this, and we will label the thing with the rule, and we will map that over all rules. What happened here? What did I do?
Index graph.
Oh, I forgot the index graph. it actually mattered. Okay, CXG graph of index graph of this. Where is our BA goes to? Oh, we didn't have it because of the canonicalization of the rules. Because we had you see what I'm saying? We didn't have the rule that we had before, the AB goes to BA rule. We didn't have that because the rules were canonicalized. So
well, hang on. AB goes to BA just doesn't do anything because it's the initial condition.
Yeah, I know. So I can change that initial condition and make it do something there. Okay, so there's that. Okay, so now let's mark on this picture which were the causal invariant ones. Okay, so let's label this with the rule and whether it was causal invariant. Let's see, what do we do here? We say with that initial condition, this is where one of these beautiful currying creatures would be useful here. Oh gosh, what am I trying to do? I'm applying this to hash, but I want to have, in addition to that, I also want to have hash itself. I don't want the select. Did I get this right? No, I definitely got this wrong. Help me out here. I think I want that. That's the labeled. Well, let's try running it. It's probably going to fail.
Wait, causal invariant Q should have the same initial condition. Well, it's not the bug here,
sure,
but
yes, for sure that. But I've got another problem here.
Yeah, I think you have at least one too many ampersands.
Okay, let's walk through it here. So this is, yes, I definitely don't want that ampersand. Okay, here we go. All right. So the causal invariant ones are, well, that's interesting. That one, okay, these are not doing very much. Can we get them to do more? If we run more steps, will we get more things to happen or not?
wait, okay, that's interesting. So all of the ones where causal invariance fails have cycles, or just are cycles.
Well, this is a pretty close to a cycle as well.
No, but crucially, it has that thing coming out of it that makes it not a cycle.
All right. Well, let's try the next case then. What should we try a different set of rules where some of them are causal invariant, some of them are not? How about we try this, and then let's say 1 goes to 1 as well. Okay. So now let's try the exact same thing there on this set of all rules, and see what we get. And I think I'm going to have to fire up my multiple processors here. Oh, let's do it.
How many do you have?
About 100. If they all fire up correctly. Okay, let's try this now. See how this works. Oh. What is that piece of absolute weirdness?
Causal invariant Q is not running on your parallel kernels.
Ah, that's because when the resource function loads, that whatever reason that definition wasn't communicated to some of the
Yeah, to some parallel kernel. Okay, well we can, but let's look at these. So these are, this is this graph. So there are an awful lot of cycles here.
Oh, hang on, wait. Oh, that's interesting. Hang on, there's one there that's a cycle and it's causal invariant, which invalidates my previous conjecture.
Yes.
But
well, maybe it's trivial that these have to be cycles.
But the ones that weren't causally invariant, I think they're not growing. Like in the earlier example, the two non-causally invariant ones were a cycle of 2 nodes and a cycle of 3 nodes, and they didn't grow as you increase the number of steps. Well, I think they're growing here if they're causally invariant.
It's not clear what was happening.
Yeah, the AA goes to A goes to B.
What?
That looks interesting. That's the most non-trivial structure of the ones we've seen, I think. The AA goes to A goes to B.
This one here?
No, the one just below it, because it has a bunch of things coming out of it.
Well, it has a bunch of transients feeding into one state, and then it just goes off on its cycle after that.
Right.
Can you guys take a crack at explaining what this is? I am lost about what that graph, what is the edge, like there's an edge if what?
If it was not possible for a particular event to occur, given that a different event occurred previously.
Is it correct that the transitive reduction process is reducing threads of time to single edges?
Yes.
Yes. So that's why a single thread of time corresponds to a single path in the transitive reduction graph.
Right.
But then how are they connected? How are threads of time connected?
Well, I think what this is saying is that there are multiple initial conditions which all feed into a single thread of time that then takes place.
Or it's not threads of time, right? It's threads of non-time, threads of impossible threads of time.
Yeah.
Yes. This
right,
is...
but I think it's a good analog for threads of time, because basically, one of the simplest ways that you can have an event be impossible given a previous event given a different event has occurred is if the first event occurs before the other one, right? Because in our models, if we exclude the possibility of time travel, the simplest case of causal exclusion is when one event is strictly in the past of the other.
But then does that make this that interesting in a way? It's telling us something that isn't that complex.
Well, this is my point is that the interesting cases are the ones where it's not just, because at some level this is just telling us about the partial order, but then it's also telling us about things that aren't just described by the partial order. It's telling us about other causal exclusions as well.
Sorry, go ahead.
No, please.
Is the transitive reduction of the regular causal graph anything interesting?
Well, it's already transitively reduced.
Yeah.
Okay. Right.
Yes, because it's just going one step at a time. Right. So it better be the case that if we do this graph here and we say transitive reduction of that graph there, okay. So it just got rid of the multi-edges, but otherwise, I think, did it? Help. What happened here? So let's take the simple
Maybe you can
graph.
label them.
Yeah, I'm
look, there was a skip. There's a skip connection quite obviously at the top there. The root connects to the second vertex, right? You see that?
The root connects to this vertex here. And yes, and the root only has one connection coming out of it. So why is that happening?
it reduced a transitive multi-edge.
Right. So in other words, you could get to this point here by going 2 steps, but it said, forget that. The direct connection is irrelevant.
Right.
Yeah.
Whereas if we then make the transitive closure of this one, okay, that's going to make a huge mess, as it just says all the places that you can go. What is in the future light cone? For every point here, it is explicitly drawing the future light cone of that point. Let's look at a few of the comments here on the live stream. It seems like there's some interesting things here.
But by the way, I mean, Tali, my point was that I'm thinking it should be possible to identify locks in these acausal graphs because they're just directed edges. They're places where you're saying if an event corresponds to one thread entering a critical section, then you're saying the other thread is excluded from entering that critical section. So the 2 events that correspond to those threads entering that critical section should be connected by a directed edge, or actually a pair of, there should be a cycle, right? There should be a pair of directed edges connecting one to the other.
Let's look at some of these comments. And
you seem unconvinced.
No, I'm thinking about it. But it's in a weird way, it's like the opposite of the branch hill graph, right? Because the branch hill graph, like, just imagine a mutex. If one thread claims acquires the mutex, the other can't, the lock, the other can't, and vice versa. They will eventually resolve though, because one will release the lock at some point. But while it holds it, there's an entanglement. Yeah.
Right.
Wait,
well,
why won't it?
Did you guys just figure out that a mutex is an entanglement?
Well, I mean, this thing about, it does feel like locks introduce branch pairs, because in a way a lock is a race, right? It's there to control a race, a data race. But it is a race, like either thread could get there first.
No, but I mean, a lock is a way to avoid that. It is the possibility of a race that is, when you represent the possible branches of a race, that is a branch pair. And I mean, in a sense, what one is saying is a lock is a way to draw some weird foliation to prevent, the branching from happening, right?
It does. No, it's still, the branch will still happen, right? Because, this is interesting. And the reason is that the threads can still race to acquire the lock. It's just that the acquisition of the lock is an atomic event, whereas if you have a more extended sort of space-time structure, you can't be sure that your edits to it won't interleave with the edits from another thread and yield some sort of nasty business you can't predict. And so you protect it with an atomic synchronization point, the lock.
Right.
So it's drawing a little boundary around some chunk of graph, and there's still a branch though. There's still a branch pair.
Yes, there is, because one side could lock rather than. I mean, it's a question of who gets the lock.
I suspect what's going on is effectively with a lock versus just the plain, race condition case, is the distinction between the multi-way system and the generational multi-way system. Because what's happening in a lock case is you're saying, suppose this region of hypergraph got updated, right? Then you're saying no other updates can get applied to anything that overlaps with that hypergraph, with that region of hypergraph. So that's the analog of a lock. But then if you then apply the maximally consistent set of space-like separated events, you get the generational multi-way system, which still has branches, as Tali says, because you can still effectively get race conditions for that for who acquires the lock. In other words, where you apply that initial updating event, affects which generational multi-way state you get. So I think basically what's happening is that the pure race condition case gives you the multi-way evolution graph, but the race condition for a lock gives you the generational multi-way evolution graph, and therefore has to do with sort of local gauge invariance and things like that.
But it's also possible that you can have two independently operating locks, right? So it's not a generational multi-way system globally. It could just be that you've drawn a kind of like little partition of your graph, and within each partition you have a generational state.
Yeah, sure. Actually, I think that you can still probably represent that with a generational multi-way system, because in general, it won't be the case that where you apply that first update completely determines where you can apply all of the others. It just places some constraints, right? And so, and that's the same as what's going on when you have multiple locks.
So explain to me what the branch hill graph is in terms of this locking thing. So you're saying branch pairs correspond to essentially races, possible micro races, so to speak, that happen. And there could be many. I mean, usually in software we write today, we try and avoid having, we try and get zero race conditions. But we're saying in this case, in the case of the universe, it's just got boatloads of race conditions. But my question would be, so then, in the software case, we usually do not consider the case of very large numbers of race conditions. But were we to have that, then the branch hill graph represents the kind of the collection of entanglements between those race conditions. What is that in software engineering?
I'm not sure it has a name.
I mean, when does one have multiple race conditions? Because usually you're talking about, these checkers for Go, and I think Rust has some mechanisms and things as well, where you're like, you're
Rust
trying to
prevents data races completely, yeah.
Right. But I mean, so when do you have a situation in which there are many such things going on? I mean, one is clearly something like this hash graph situation, where you're trying to make, where you've got lots of different transactions that happened, and you're trying to make consistency between all those transactions, and you'll inevitably have the possibility of having transactions, be injected into the system in different orders. But where else do you have in software engineering? Where else do you have kind of a large collection of race conditions all simultaneously possible?
Well, the traditional distributed computing case, I think, encompasses that, right? Because like
any kind of distributed system, like clustered system, right?
Well, I understand that you can have it, but you usually try to avoid. I mean, you're saying in writing a program, you're trying to avoid that. So my question is.
Well, no, in writing a program where you have multiple processes talking to each other and interacting with locks, you're preventing the race condition, while in a distributed system, you're allowing it to happen and then reconciling afterwards.
I would disagree with that. I would claim that what locks allow you to do is to tame race conditions so that you, as a programmer, take on the kind of algorithmic burden of ensuring eventual consistency. So you say, for example, I'm going to lock some data structure, like a list, and add things to it. And it's okay that the list could end up in different orders, depending on which thread won a particular lock. And you're just taking it on yourself, right? Whereas, and you're drawing a box around the delicate part and then proving for your own benefit that the rest of it is manageable in non-determinacy, which is also true of distributed systems.
But so what is the analog of the branch hill graph, again, in these distributed systems? What is in the case of one of these, well, there's one thing, do we know what that might be? And how does that relate to, and then what is the foliation of the distributed system? What's the analog of foliation in the distributed system?
I have a question about foliation to even answer. So when you foliate quantum states, are you identifying them all with each other? Like, it's a foliation in time, right? Branch-like hypersurfaces foliate in time. But within each slice, different quantum states they're not considered to be identical, right? They are seen as different.
They're a superposition. I mean, that is, those states are being combined as part of one, one superposition, one single superposed quantum state. Jonathan, do you have a different way to say that?
No, I think that's the right way to say it. I mean, basically what the observer is doing in order to have a causal invariant representation is they're taking all of the possible outcomes of the superposition, and when they perform a measurement, they're saying somehow in their own internal representation they end up being the same. And so the completion procedure is kind of the minimum thing that they need to do in order to ensure that happens. So yeah, I think it's legitimate to say that basically in the same way as the foliations of space-time define simultaneity surfaces, the foliations of branch time define essentially equivalence surfaces.
Well, or superposition. Okay, now let's talk about the quantum computing case. What is the analog? So we're talking about distributed systems, and which are essentially distributed in space-time. Now we talk about quantum systems, where essentially we're distributing in branch hill space. Is that a true statement? What's the analog between a distributed system and a quantum computer in this model? I'm
sorry, internet connectivity died. I didn't hear anything at the last minute.
Jonathan, did you hear that?
I did. Sorry, I was answering your previous question. I just posted the thing in chat.
Oh, okay.
So there's this. It appears there's this notion of sibling states versus non-sibling, or sibling tasks versus non-sibling tasks in the context of identifying race conditions. So sibling tasks are tasks that are produced by a common parent task, and so I suspect that the analog of a branch hill graph is something like a representation of of connections between sibling tasks.
Interesting. Okay, so you're saying let's go back to our dictionary, wherever that was, that we may have branch hill graph is possibly sibling tasks. So you're saying sibling tasks or sibling?
Yeah, right. So okay, in this, I've only skim read part of the paper, but basically what it's talking about is that you're trying to resolve the situation where you want to have local synchronization between successive tasks that have dependencies on each other, and so then in order to be able to resolve that, you have to basically map out dependencies not only between tasks that were created by the same parent task, but also tasks that were created by different parent tasks. So you have to go, back up the ancestry tree, so to speak. And so what they're doing basically seems to be a construction of branch yield space, but in the context of identifying data races.
That does seem like that is the notion of ancestry there doesn't necessarily correspond to the notion of ancestry in the multi-way graph, right? Because that's parent thread creation and ancestry rather than, or task creation ancestry
rather than this possibility of inconsistency. But
right. But I mean, well, one way you can get an inconsistency is by having tasks that have mutual dependency that end up disagreeing. Right.
Explain.
So if we have the situation where you have one way that you can have a failure of local synchronization is you have say a parent task that creates two sibling tasks, and eventually they end up disagreeing about something like like what time it is, and then eventually you have that's then a conflict that you have to resolve.
That I would make. Yeah. Sorry, go on.
No, please go on, Tali.
Well, the claim that I would make is that I think if we define things suitably, the only source of indeterminacy is timing, right? Like deterministic algorithms, or at least what the processes do is deterministic. And then the only kind of like fudge is timing stuff, like caches being warm or not, RAM being like whatever. Networks having latency. And so that's the only source of branch pairs in a model of distributed computing. That would be my claim. That's excluding failure, right? Failure is a different topic. I don't really know how to handle failure. But,
that's the same thing as saying there's a single deterministic rule that applies, but the question of what it's the same thing as in the hypergraphs. You're applying some definite rule. The state that you may be in may be different because of the order of other things that got applied and so on.
Yeah.
Well, what Tali is basically saying, I think, is the statement of causal invariance. It's saying if you have causal invariance, then all you need to know in order to define your hypergraph is the individual timings of the updating events, which tell you the foliation of the causal graph, right?
Yes, I think that's
But if you don't have causal invariance, then that isn't true.
Okay, I want to come back to my little question about quantum computers and the analog of what, if we're starting to understand what a branch hill graph might be in distributed computing, give me what is the analog? How do we think about the analogy between quantum computing and distributed computing? Because what we're saying, that's a Jonathan question.
I don't know enough about distributed computing to say.
Well, but I mean, what we're identifying here is that these various race conditions, these sibling tasks, whatever they are the way of distributing different, trying to understand what we're not used to thinking about these sort of foliations of distributed computing in the same way.
Well,
whereas in the quantum computing case, we're thinking about, what do we do when we send in a quantum computer, when we're sending it through a series of gates and so on. You're having this whole this whole superposition state that you're doing things to. Whereas in the distributed computing case, we haven't tended to think about it that way, but I think there must be a direct analogy between these.
Well, I mean, the only analogy I can think of is the totally trivial one, which is saying that the difference between what a quantum computer is really doing, and people don't conventionally think of quantum computers this way, but I think it's a perfectly reasonable way to think about them, is that they are basically, they're evolving both possibilities of the race condition, right? If you have a race condition where
sure,
two threads could do a particular thing, the difference between a quantum computer and a distributed computing system is that the quantum computer does, but in the quantum computer, both threads.
Right. I mean, that is a commonly said thing about quantum computers, but I'm trying to understand whether we can make that more precise in this setup, and whether we can really understand more, whether we can use what we understand about quantum computers and superposition and so on to apply it also to the case where we're just dealing with, standard distributed system. But
I don't think I can say anything that Tali hasn't already said, that basically, race conditions are branch pairs.
Fair enough. We've got a lot of interesting comments on the live stream here. Let me just take a look at a few of these. Oh my gosh, let's see. In physics, would gravity work like a sort of vector clock between all points in space to create a type of synchronization? Not sure. Okay, let's see. We're going back a little bit ways here because we haven't been paying attention to this. Okay.
Once we're done with our viewers' questions, I might have a question of my own, if that's
Please.
allowed.
What's that? Okay, so there's a comment here from Laurent. You define synchronization of distributed systems using time which is external to the system. You exploit an external property to achieve synchronization. You can't do that in your physical model, but I don't think in distributed systems, I mean, the interesting case is where you can do internal synchronization, I think.
I would agree with that. So like some systems do need like atomic clocks, like Google Spanner famously did, but many don't, because they like vector clocks are an example of a kind of a proper time, right? Like it doesn't matter whether a particular clock runs slowly or fast. It's just it's relative. Yeah, it's the causal relationships that are tracked.
Someone who's suggesting HPU, a hypergraph processing unit. That's amusing. Let's see.
It's a good rebranding of quantum computers.
Right. Let's see. Shared memory, Brian says on live stream, seems to imply the existence of a cosmological rest frame that all processes can access. I don't think that's true. I think that there's no, I mean, the whole point is that you can have different parts of the, the shared memory can correspond to the spatial hypergraph, and different, I think the interesting case, and the case that's probably relevant for practical distributed computing kinds of things, interesting thing that probably hasn't been studied as much as it could have been is when it actually matters that different parts of the shared memory can be accessed at different speeds by different processors and so on.
Although actually, there's an interesting question I'd like to pose to Tali about that. So the thing you were talking about earlier about blocking, so where you set up a wall in your multi-way evolution graph, and then you say we're not going to, sorry, in your causal graph, and we say we're going to slow things down so that everything kind of synchronizes at that wall. Are we not basically assuming, in order to set up that wall, we have to assume that there's a sort of a cosmological rest frame or something like it, right? We have to assume there's some global external time that these things could query, or am I misunderstanding?
It's a good question. I think the actual guarantee that's made is that once we've hit that point, the only thing that threads know so what happens really, I mean, physically, is that the threads kind of all sleep when they get to that, except for the last thread to come along. It keeps going, and the others then wake up. And all that this does is it allows threads to guarantee to themselves that every other thread has reached the barrier and passed it. So there can be fuzziness at that point, right? They don't know when exactly the other threads have started, but they just know that the past is the past from the perspective of the other threads.
See, I'm just trying to parse the large number of interesting comments here. Let's see. How is a semaphore used? What is the relationship of a semaphore to what we're talking about here? Anybody want to
Well, semaphore is just an example of kind of shared state that's used for control to some contended resource, right? So, or for synchronization. So, like a Boolean that two threads used as a mutex, that's a semaphore.
Well, and in our case, what that is saying is when we draw these causal edges, we're drawing them because there is an effect of, because there is a piece of state, so to speak, that is shared between these events. So that's in a sense that the semaphore is the piece of shared state between the successive events. Is that a fair statement?
There's something, I'm not sure if it's relevant to trying to translate into physics terms, but if you have a lock or a mutex that's driven by a semaphore or whatever, you generally have the option when you try to access it and you can't because it's locked by another process. You have the option as a programmer if you want to block until it gets unlocked or just proceed and do something else instead. I'm not sure if that has an analog, that choice, or those two possible methods have an analog in physics terms or not.
It reminds me a little bit of this choice of a local gauge, because it's like once one little piece of space chooses among all these different options, others can't, but they can choose something slightly different maybe.
Yeah, I agree. I think it's basically a local gauge invariance story.
Sorry, what was I? Excuse me. I was reading these comments here. What's the local gauge invariance story? Jonathan, what was
Sorry, no. I mean, Tali was just saying that so with Jesse's question about when you have a mutex or something, and a thread has a choice. If it sees that a lock has been put on a critical section, it has a choice to either wait or to do something else. That's the local gauge invariance story. Is you've placed an updating event in the hypergraph, and then now other updating events have a choice to make about where they're going to apply their events in a way that doesn't conflict with that.
Yeah, that's really interesting. Okay, so where are the gauge bosons? That's not a completely silly. I mean, I'm not saying that frivolously because if what that's saying is, I mean, the communication of information by virtue of the sort of correlated choices of which mutex to pick.
Well, maybe they're the semaphores, right? Maybe the gauge boson, because I mean, the semaphore is the thing that, my understanding is the semaphore is the thing that tells you, this person chose to enter the critical section or something like that, right? Or in other words, this person chose to apply this updating event in this particular region of the hypergraph. So then, in order for that to be able to constrain what other updating events can be applied, that information has to get propagated out. And so in the distributed computing case, that would be via a semaphore. In our case, it's presumably via a gauge boson.
But what we were thinking before is that the semaphores are pieces of shared state between events. So how does that work?
There's another thing to inject. There's something with more structure that I should mention, which might have a beautiful kind of analog here, which is a future. So a future is a sort of like delayed computation. It's a computation that will happen when something else is ready, but not now. But you can still maintain a handle to it.
Is that like a promise, or is that different?
I think they're the same.
Okay.
I have no idea what that would be. I mean, it's like a little chunk of, I don't know what it is.
So let's think about that for a second. So that's a place where, oh gosh, what is
Wikipedia
that?
says they're often used interchangeably, but there are some differences.
Okay. My bad.
No, but it looks like the differences are subtle.
I don't know. Right. So.
Okay. Well, can I inject one last thing?
Yeah.
This is actually the thing, Stephen, that I mentioned when we chatted on the weekend and sparked this whole thing, I guess, was the cap theorem. Which is a theorem that describes the properties that you can have for a distributed database. You can't have all of them. You can only have 2 of the 3 properties. And those are consistency and availability and partition tolerance. You might as well look at the
I'll
web
look
page.
at the page here.
Yeah. And it feels like that the partition tolerance is something to do with causal disconnection. Consistency is something to do with branchial graph distance. I'm not sure what availability is. Something to do with space. It's like every node can reach you.
So what's the point here? The point is that you're saying for every database, just as a matter of sort of the structure of causal graphs, it is not possible to have all of those properties. Is that right?
Yeah.
And this is a thing that's true about any causal graph that defines a partial ordering, is that these properties are not consistently, cannot all exist. I mean, is this true of any partial order?
I'm not sure.
Okay. So what is your contention is that this has some analog in, I mean, so in other words, if there is a way of thinking about different possible, different possible properties of a partial order.
Well, I was thinking something, so a very loose kind of mapping would be something like, and this is very impressionistic, but it'd be something like consistency is some notion of forming a classical thought. If you imagine it's the ability to do completions, right?
Yes.
Availability is, I don't know, partition tolerance, like it feels a little bit like you get close to a black hole, you know, the point that you made about not being able to form a classical thought after you pass the, was it the causal horizon? I can't remember. The
entanglement horizon.
Entanglement horizon.
Yeah.
Right.
So consistency, the idea would be, you know, some kind of classicality, getting to classicality by consistency somehow. Yeah, I'm not sure. I mean, I think it's worth understanding. Well, listen, I wanted to come back to.
I suspect availability probably corresponds to something like the statement that every event has to have some causal connection, you know, has to have some causal predecessor, unless it's the initialization event.
Okay. But so what kind of a thing? I mean, you know, the thing one's hoping. Okay, actually, Jonathan, can you make a comment? So the generalization of things like Bell's inequalities. What is that thing called CRS? What is that thing called?
CHSH, which is that's the modern form of the Bell inequality.
Can you say something about what that is and how that works?
Yes, I suppose. I mean, I'm not sure if it's super relevant to this particular case. It's the CHSH experiment is just it's a generalized version of the Bell experiment where you don't, you know, the angles can be kind of arbitrary in the, you know, in the polarization in your two detectors.
Okay, fine, but that's a detailed feature. But I mean, what's the way of thinking about that in terms of different pieces of the multi-way graph, for example? How does one think about what property of different pieces of the multi-way graph is the thing that leads to essentially the violation of Bell's inequality or this CHSH thing? And
okay, yeah, sure. So okay, so it's worth just briefly summarizing. So, okay, so in the same way as the CAP theorem gives you kind of three properties and it says choose up to two, Bell's theorem does exactly the same thing. So it says you can have locality, you can have realism, and you can have determinism in your, or you could in principle have those things, but again, you can only choose up to two of those. So in the context of conventional quantum mechanics, you know, locality means just, you know, events that are, you can't have sort of spooky action at a distance. Realism means that there is a kind of objective reality to the wave function, even in the absence of observation. And determinism means that, you know, well, it means determinism. It means that you have some, you know, hidden variable interpretation of quantum measurement and so on. And we know that all three can't be mutually consistent with violation of the CHSH inequality. So in the context of the multi-way system, locality, you know, locality is a spatial statement. So, you know, locality is basically just the statement that you can't have, if you have pure spatial locality, it's really just saying that you can't have non-trivial causal connections between different multi-way branches, right? It's saying that all of your causal connections have to be localized in space and they can't kind of move about in a non-local way in branchial space, right? then determinism is really the statement that there's a single thread of history. So the thing is, both determinism and causal invariance, both determinism and realism are kind of specifying different aspects of causal invariance, right? Realism is saying that there is kind of a definitive reality, or there is a definitive causal graph, I suppose we could say, and determinism is the sort of single thread of history kind of idea, which we know is also related to causal invariance. And so it's forcing us to pick between these different aspects of causal invariance and multi-way evolution.
So, I do agree that there is it is conceivable that the CAP theorem is related to something like the Bells inequality story. We don't see quite how to get there right now, but it doesn't seem hopeless that there could be a connection. I still want to come back to, gosh, there's so many interesting comments here. Somebody's commenting that distributed quantum computing seems to be really hard to achieve. That's an interesting comment.
Doesn't having entanglement make a lot of things easier in a distributed sense?
Well, you mean that you are forced to be, because you've got entanglement, it's kind of there's no way of saying, if you want the quantum computer to be operating in any kind of quantum way, you can't just say, I'm going to resolve every lock. I'm going to resolve every race condition, so to speak. I think.
But Jesse is right that at some level, entanglement gives you kind of the ultimate mutex, right?
Right. You don't need a lock at all.
Because you have no choice but to have the thing entangled. It's like if you were to operate a lock, to require the thing have a particular sequence, then you've basically reduced it to a classical computer again, haven't you? Am I missing something there?
No. I agree. It's what Jesse is proposing would no longer be a quantum computer in the conventional sense in which people mean it. But it does give. He's right in the sense that I think it does give you a potentially interesting way of doing regular distributed computing by having effectively mutexes that are enforced by physics and things like this.
Right, or a zero transmission delay network.
Right.
Well,
yes, that's true. Right. Okay, there are lots of questions here which I'm not able, or lots of comments that are interesting. And we're also being told that we're sort of out of time. And the pity of this is that we haven't managed to get to, I just want to push one more time the thing that I really think is going to be, let's summarize where we think we might be able to get. And again, we've been sort of, this is a first effort talking about these kinds of things. First thing is to really get this dictionary nailed down of what the correspondence is between sort of concepts in distributed computing and concepts in our model for physics, with the hope that we can find ways to use intuition from one side of that picture to be useful in the other side of that picture. And I think, my contention is that this question of what are useful reference frames to consider is something that is going to be different between the distributed computing case and the physics case, and that there will be some useful correspondence between those two things. I think then the other possibility, is to use what we understand from physics to give us ideas about how to formulate ways to think about distributed computing that make it easier to think about distributed computing. In particular, dealing with this kind of bulk ambiguity idea, which we're dealing with through reference frames and so on in the physics case. And I suppose the bonus thing is just this problem that I've been really curious about for such a long time, which is sort of how to think about the evaluation front. So the case of this, that this year is the centenary of the invention of the combinator, and when you're looking at combinators, you often have these non-terminating. I'm sure we can pick one out. Let me just find one. A non-terminating combinator expression, and I don't know whether one should care. It's been 100 years that combinators have been around, and they've not been used for practical computing. There's a version of combinators which is used, but it isn't the it isn't really letting combinators sort of get released into the wild, so to speak. And let's find a combinator thing. So
does Stephen, a quick question, does multi-way system support replace all as a kind of rule engine, right? Or as a rule system? Just ordinary expressions.
That's a good question. Jonathan, do you remember? We certainly
it doesn't it doesn't have a shorthand for it, but if you look at the full form, so multi-way system, in multi-way system, everything is ultimately represented in this long form association. And in the evolution function and the event function, you can put any arbitrary expression, including things involving replace all. So that you can do, but we haven't written a shorthand for it. I should probably do that. And by the way, you've reminded me that we support periodic boundary conditions for the cellular automaton case, but not for the substitution system case. And we should probably do that because it would make the dining philosopher's problem a lot easier to represent.
But this is so, I mean, we don't yet have multi-way systems for combinators, do we? I mean, we don't have it directly. We could certainly do it with your long form version.
Right. You emailed me about it last night. I haven't implemented it yet.
Okay, fair enough. But I mean, just to give an indication of what goes on here, I mean, these are combinators, and they have they have these reduction rules. And the point is, depending on the order of the reduction rule, different things will happen. Depending on the order in which the reduction is done, different things will happen. Sometimes they will. Sometimes there exists an order of the reduction rules will lead them to a fixed point. Often it never gets to a fixed point. And I don't know whether this is useful for practical computing. I mean, we've been, these things have existed for 100 years. They were kind of, their history is somewhat entangled with the history of lambda calculus, but they're sort of a more pure form of something like lambda calculus invented before lambda calculus was invented. The reason people find these very hard to understand is this notion of what is the evaluation front of, in what order do you do the reductions? Does anybody, Tali, do you have any comments on this?
No, I do remember putting together like a function long ago that would visualize the causal graph for a recursive function, and it was very interesting. Other than that, I have no comment.
Okay.
Yeah, I agree.
I mean, so in general, one of the issues is, and this is something that comes up in sort of the functional programming story, is, debuggers for functional programming, it's more complicated to see what's going on. If you have a procedural program where you're just going step, 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 in a sense, the causal graph is really straightforward. Maybe you have a loop. It's just got some, something going back in the causal graph. But in the case of these things where you are doing sort of progressive evaluation of a symbolic expression, the causal graph becomes something quite complicated, and it's quite hard to visualize, quite hard to understand what's going on. And as I say, I've been interested in seeing whether there's a way to do this for. I mean, it's also related to the question of sort of visualize the complete execution history of a functional program, the related kind of thing. And what is the, can you pick out, well, it's again a lot about dependencies and causal graphs and so on.
Actually, can I make a comment about automated theorem proving? So, yes. One common question that people have about ATP and actually about the automated theorem proving functionality we have in the Wolfram language, things like find equational proof. People often ask, is the proof that gets returned kind of the optimal proof? Is it definitely the shortest number of steps? And the answer is no. And the answer is no for a very good reason, because the length of the proof depends on the order in which you apply the completions, right? It depends on which critical pairs you complete and in what order. And different completion orders will lead to proofs of different length. And there will be one that's optimal, but we don't look for the optimal one. We just kind of do the completions in any old order. And we assume that what we lose on kind of space complexity, we gain on time complexity, which is generally true in the ATP case. But the point is that actually each of these different orderings of critical pair completions is basically a different evaluation front. It's a different foliation of the causal graph for this automated theorem proving system. And so the statement that we don't give the user the shortest proof is the statement that we don't want to have to do the algorithmic work of kind of computing all possible reference frames and seeing which one produces the shortest proof. We just pick kind of the cosmological reference frame and we go with it.
what does it mean? What is the reference frame of the shortest proof? What does that correspond to? Is that a shortest path thing is that like a path of least time or something? What is that in the physical case?
It's a little bit complicated, right? Because it's it's like it's the simplest sequence of measurements that you would have to make in order to be able to agree on a particular classical outcome, which is a complicated story about branchial hypersurfaces.
The shortest sequence of measurements to agree on a classical outcome.
Because basically, okay, so each foliations of the multi-way evolution graph are like different measurement sequences, right?
Yes.
And so what you're really asking for is what is the particular sequence of measurements that we make? Given that we want to obtain it's kind of the opposite problem to the one you're normally solving and doing the quantum measurement. But you're saying, suppose I want to isolate this particular multi-way state. This is what I want to agree on as the classical state of this system, right? And then we're asking, what is the shortest sequence of measurement operations in order to get a foliation that agrees that is the state of this system? But doing that requires evaluating a whole bunch of different multi-way foliations, so we don't bother.
No, but I mean, what you're asking, to what extent is that saying what's the minimum set of quantum measurements you need to make to establish some feature of a quantum system, right? Because you can make a different collection. What set of quantum measurements do you have to make to completely specify the system somehow, to determine, I mean, what's the way of thinking about that in quantum mechanics? So
right, I mean, it's like this. Well, I mean, it probably has a really nice interpretation in terms of quantum computing and in terms of quantum complexity, because it's like you're saying, because in general you're not going to completely nail down unambiguously a single state, right? In practice, because of experimental error and all kinds of other things, you're probably going to end up with a small bag of states, and how large that bag is basically your quantum error. And so things like the BQP complexity class, the bounded error quantum polynomial time complexity class, are talking about the efficiencies of these procedures, given that you have a bound on how many states you want to end up in your bag.
Yeah, I mean, to me, it's really interesting. Look, the main meta point that's coming out of this discussion is we've got these different things going on. We've got what's happening in physics, particularly in our model of physics, distributed computing, automated theorem proving, quantum computing. A lot of the kind of conceptual issues are the same between these different fields, and that's always kind of a cool thing to discover. There's that again. I'm in a sense, I think the lowest hanging fruit here is the sort of purely constructive issue of thinking about, what does this mean for a way to think about distributed, programming distributed systems. Okay, last few comments here from the isn't causal invariance tolerance in the CAP? Don't know. Does anybody want to comment on that? Tali, Jonathan? Causal invariance as tolerance in CAP.
Do they mean partition tolerance?
Not sure.
Yeah. I mean, the analogy there felt like the partition, or at least the slowing of messages, kind of reminiscent of sort of time dilation near an event horizon, right, or near a black hole. So,
yeah, I agree with Tali that partition tolerance does seem to be basically saying you can have event horizons and it doesn't sort of collapse your whole causal graph.
What was the thing, Jonathan? You were talking about some distributed computing.
REO.
How's it spelled again?
REO. Tali, have you heard of this thing? I learned about this today. It's a coordination language used in concurrent programming, apparently, that represents things in terms of partial orders on hypergraphs. I
is something
else better. Sorry, go on.
This looks really interesting. I'll look at this. There's a similar thing called timely data flow, which a lot of it involves kind of like building causal graphs, I believe, so that you can do diffs. Like if your computation depends on something that changes, you can recompute it cheaply. I believe that's one of the main ideas.
What is that thing called?
timely data flow.
Okay. I mean, what is the relationship? I mean, the multi-way diff is another timely data flow. Okay. Oh boy, so many different formalisms and so on.
Actually, that's an interesting. Yeah, I hadn't really thought about that before. But the multi-way diff is basically a measure of deviation from classicality.
What do you mean? Okay, what is the multi-way diff?
The diff between states on different branches of the multi-way system. The larger that diff, the greater the deviation from classicality, effectively.
Well, that's true. Yeah.
The more extreme your completion procedure is going to be in order to resolve those states.
Well, you're saying that the resolution of diffs is like a completion procedure.
I think so, yeah.
Yeah, I think that's right. And so what does, I mean, when we look at the multi-way graph, what is its relationship to a Git-like graph?
Well, I think Max seems to think it is just a Git commit history, which I think is probably right.
So what do you mean by that? You mean that the multi-way graph, see, this is another crazy analogy. I mean, another crazy thing.
The branches in the multi-way graph are literally like Git branches, and then when you do merges and things, that's the analog of either natural merging or completion.
And what's a merge conflict?
So a merge conflict would be a case where I guess you need to do completion.
Right. So the point is, it's not causal.
Exactly.
What's that?
I was just joking. Where God. Okay. No, just a joke about moment has passed.
But I mean, so you're saying the existence of a merge conflict is a violation of causal invariance, basically. That's what it means to have a merge conflict.
Yeah, exactly. Because like spatially separated edits by human beings can be merged naturally, right?
Right. A merge conflict is a declaration of ambiguity.
Yes.
Right. Which is where we'd have to do a completion.
Right. So that's interesting. Okay, so this is yet another formalism. I mean, again, there's another thing we really need to inventory is all these different formalisms, which are, I just don't know. So we talked about Rayo, we talked about timely data flow.
There's also all the process calculi that are, the formal models of computation.
Yes, I know. And there's also Petri nets are somehow related to all of this somewhere.
Well, I mean, if someone ever builds a Petri net function, then we can just pop it into multi-way.
I know, we have some Petri net functions. The problem with Petri nets is they're a mess. I mean, Petri nets were originally, their original concept was to model things like chemical reactions, where you have sort of, instead of being a function where you have multiple things coming out and one thing coming out, you can have multiple things coming in and multiple things coming out and so on. So
we have a summer school project, don't we, from last year that has a Petri net function?
Yes, I think so. I don't know how good, how effective that is. We should look it up.
But I like Tali's idea of integrating that into multi-way system. That seems like something worth doing.
One question I have is when you have an arbitrary function into multi-way system, how does it know about causal dependence? Like it doesn't have a notion of the space inside the state, right? So it can't know.
Yeah, right. So you have to specify this thing called the event decomposition function as part of the association, and so the event decomposition function we have this natural specification of events, which I'm sure you've seen, which is it's a list that consists of the input goes to the output, then the particular instantiated input, and then a sublist that contains the prefix and the suffix in cases where that makes sense, or in cases where it doesn't make sense.
Let's be explicit here. So this is now saying the big complicated thing is these things here. What is it? So the state evolution function, the successors to a given state, the state equivalence function, where the two states should be considered equivalent. Then, what is this? The state event function, the list of events applicable to a given state.
Yeah, but anyway, the thing I was particularly talking about was this event decomposition function. So given that specification of the event, given this list that specifies the event, there's a function within the association that takes that event specification and decomposes it into the events that created elements in that state and the events that destroyed elements in that state. And from that, you can work out, because as long as you know the creator and destroyer events, you can work out the causal relations. So that's how it knows.
That's really cool.
This
is very general. I mean, this is a beautiful function.
Yeah, well, we argued about how to design this for a long time.
Right. Well, and the good news is it's been battle tested by having been applied to particular kinds of, kernel functions, so to speak. And I guess we have barely even looked at the case of, for example, cellular automata causal graphs.
Yes.
We put them in here. Did we look at Turing machine ones?
We thought about it, but I never implemented them. I'll do that at some point.
But and non-deterministic Turing machines are another case. What was the thing?
Well, actually, all Turing machines are kind of non-deterministic in a multi-way system.
Right. So just mention your correspondence between this and the quantum computing system.
Okay. Well, in how much detail do you want this?
Well, first of all, the basics.
Okay. So the our quantum computing framework, our nascent quantum computing framework, basically there are two fundamental objects. There's a notion of a state and there's a notion of an operator, and everything else is kind of just superstructure around those ideas. And in particular, you have the notion of a discrete operator, which is like an evolution, and you have the notion of a measurement operator, which is a measurement. So in the multi-way system, our state is a particular hypersurface in the multi-way evolution graph, which defines a linear superposition of eigenstates. And then the analog of the discrete operator is then a collection of updating events that get applied to that quantum state. And then our notion of a measurement operator is a collection of events that don't evolve the system forwards in time, but rather collapse that state. So in other words, they're multi-way evolution edges that don't connect two neighboring hypersurfaces, but rather they're multi-way evolution edges that connect states on the same hypersurface. And that's what's involved in this sort of measurement procedure. And so there's quite a neat sort of conversion procedure between objects that exist in our quantum framework and objects that multi-way system can manipulate.
And the result of the measurement is the
path
weights.
Yeah, right. So if you apply a bunch of these updating events that are all on the same hypersurface, it has, this is the completion procedure. So you end up with just a single eigenstate. And so the result of that measurement is that in the multi-way case is an eigenstate. In the quantum case is a data distribution that corresponds to the eigenspace. And given, as you say, given the multi-way path weights that sort of that flow into the eigenstate that you collapse down to in the multi-way system, you can extrapolate what that data distribution has to be, because basically the path weights define the amplitudes.
So let's say we take Shor's algorithm in the quantum computing case. Do we know what that looks like in the multi-way? I mean, do we know what is the core idea of Shor's algorithm as implemented in the multi-way system? Do we understand that?
No, I mean, I can't give you anything more than a high-level explanation. Ruhi is currently working on implementing Shor's algorithm, and it seems to have made pretty good progress over the last few days. So
in what, in the multi-way case, or in the
no, in the pure quantum case. But once we have it working in the quantum computing system, I have some helper functions that can convert the circuits into multi-way system rules, and so we can then see what it actually does. I
mean, I want to just say that how cool I think it is that we can actually take, the quantum computing case and literally translate it into this model effectively. I mean, that's a very, and we should be able to see, and the fact that in this model, we have a much more operationalized version of measurement. So we should be able to see, we should be able to answer the question. I mean, for example, in the case of Shor's algorithm, doesn't Shor's algorithm in the normal way it's set up just have one measurement that happens at the end?
Yes, exactly.
And so the version of that we will end up with will have one measurement that has been decomposed into multiple branchial events, so to speak, or will it be what will that look like?
Well, it's possible to do exactly the same thing, because you can have your measurements you can apply all of the completion rules as a single generation, right? So in that sense, it's possible just to have one single measurement event. But you could also split it up into multiple measurement events if you wanted to, in exactly the same way as you could in Shor's algorithm. You can measure every qubit individually if you want, but you can also apply an overall measurement operation to the whole collection of qubits.
So what I'm wondering is there a compiler, just as we're making a compiler that goes from a given unitary operator down to a bunch of gates, right, for the time evolution part of it? Is there a similar kind of compiler that we can make for the measurement part of it?
In the quantum case, yes, I think so. I mean, that's effectively what you do when you do this circuit compilation stuff. Is you decompose, you treat the evolution part and the measurement part separately, and you do separate decompositions on the two, and then you combine them.
Yeah, so there's already a decomposition of the measurement part there.
Yeah, I mean, it's the same kind of thing, right? It's also just a kind of fancy, matrix factorization problem, just of slightly different kinds of matrices.
Right. Oh, somebody is commenting here. I think one last comment here about IOTA, which is another blockchain that. Yeah, this is another thing. I mean, I know we've interacted with these guys for purposes of talking about blockchains. I mean, I think there are a bunch of these. Gosh, there's so much to understand here. It's really, really interesting. Yeah, lots to understand about the correspondence between, and I wonder, again, I keep on coming back to my prejudice about what's going to happen is that this intuition about reference frames and thinking about things in terms of reference frames is going to be really useful for thinking about programming in, and I also want to understand what the analog of these foliations is for. I mean, I think for like these hash graphs and these other kinds of distributed consensus type algorithms, this notion of a foliation is like turning it into a blockchain, so to speak. That's what I mean, to take the thing which is a network and turn it into a sequentialized sequence is, that's the analog of our foliation of successive moments of time, so to speak. All right, we should, yeah, okay, a comment from MetaConstruct on the live stream. We need an army of folks studying category theory to formalize or generalize all of this. Yes, we were thinking maybe we'll do another one of these with somebody who's been involved in the categorification of things. I always worry about that stepping up the level of absolute abstraction, but that may just be because I'm not used enough to categorification.
It'll get category.
Yes. I was suggesting a person who I actually know from a long time ago, from Algorand, who yes, that's I haven't seen him in oh boy, 35 years. Yes. All right. Well, we should wrap up here, and we're still in the general framework of how one figures ideas out. This is in the high temperature, still very nascent phase of trying to figure things out. This was sort of our first effort at this question of sort of the correspondence between distributed computing and our ideas about physics. And I have to say, my main conclusion is there's lots of interesting things to figure out here. We didn't figure too many of them out definitively here, but I think we raised a bunch of great questions, and I look forward to continuing this. So, well, thanks to folks here, Tali, Jesse, Jonathan, and thanks to people on the live stream. More comments than I could even keep up with here, and a lot of good suggestions. So this is an area where there's lots of great things to do. So maybe some of the people who've been following us on this live stream can think about this themselves and start figuring out interesting things. That would be great. All right. Well, sign off for now. And I think we have, gosh, are we doing yet more live streams? At some point I got to go back to my day job, and we may be doing some live streams about, oh yes. Tomorrow we're doing quantum spin and charge. And that's, I think we're making good progress there. Let's see whether tomorrow at 3:30 Eastern, let's see whether we can figure out what quantum angular momentum is. I think I give us about even odds of making that tomorrow. So Jonathan thinks he's already figured it out. I know that. So even odds for being able to figure out what quantum angular momentum is. I mean, it's kind of crazy that we can even consider doing something like figuring that out in a live stream, but we've got a fertile area here. And then on Friday, I guess I'm signed up to do something which hopefully is lower difficulty for me, which is a science and technology Q&A for kids at 3:30 Eastern also. All right, well, thanks for joining us, and see you another time.
Thanks.
Bye.
Bye.
Bye.